Hello there and welcome to Science for Sleep, where you can let the busyness of the day loosen its grip while we wander slowly through ideas that don't demand anything from you. Tonight we're settling into something that might sound ominous at first, though it has been quietly surrounding us since the beginning. It's an idea that sits just beyond what our eyes can reach, tucked into the spaces that light never fills. We're going to spend some time with the puzzle of dark matter, but we're not rushing toward answers or solving anything in a hurry. We're simply drifting through what makes this invisible ingredient of the universe so strange and so deeply important. Before we ease into it together, I'm curious about where you're listening from right now. Is it late in your part of the world, or are you unwinding in the afternoon, looking for a bit of calm before tackling whatever else waits for you? Wherever you happen to be, I'm glad you're here, and if you find this little journey soothing or helpful or simply a nice way to let your mind slow down, I'd be grateful if you tapped the like button or subscribed, since it helps this sleepy corner reach others who might need a gentle companion in the background. Now that we're settled, let's take a breath and step quietly into the story unfolding between the stars. Most of the universe looks empty from our perspective. When you look up at the night sky, you see sprinkled lights, small dots scattered across a vast background that seems more like nothing than something. It's tempting to imagine that the space between those points of light is just emptiness, an enormous dark canvas. But astronomers have learned over decades of measurements that this darkness isn't just void. Something is there, not glowing, not interacting with light, not showing itself in any direct way. It's present through the only thing it apparently cares to influence, gravity. And gravity, patient as always, leaves clues. That is where our story of dark matter begins. It starts with a question asked quietly by researchers who noticed the universe wasn't acting the way it should have acted if it only contained the matter we can see. Stars were moving in ways that seemed to ignore the normal rules. Galaxies were holding themselves together too tightly. Clusters of galaxies were behaving as if bound by something with far more mass than anything visible inside them. These weren't small inconsistencies, they were enormous, and they whispered that something unseen was pulling the strings behind everything, shaping the structure of the cosmos while never stepping onto the stage itself. The first hints of this came from simple observations, the kind that involve measuring how fast stars orbit around the centres of galaxies. According to what we understand about gravity, the stars farther from the centre should move more slowly, yet when astronomers actually measured their speeds, something unexpected appeared. The stars in the outskirts weren't slowing down. They were moving just as fast as those nearer the centre, in some cases even faster. That should have torn the galaxies apart, but the galaxies stayed whole, as if wrapped in something massive enough to keep everything together. The visible matter wasn't enough to explain that, not even close. Something else was offsetting the centrifugal push of those fast-moving stars. The question then was what? It wasn't the kind of mystery solved by simply looking harder. Telescopes kept improving, instruments became more sensitive, and maps of galaxies grew more detailed, but the extra mass continued refusing to show itself. It didn't block light. It didn't emit any. It didn't scatter it. All the usual tricks astronomers relied on for studying distant objects suddenly ran out of usefulness. Yet the evidence kept piling up that something was exerting gravitational influence. Something enormous. This left scientists to work backward, not by detecting the thing itself, but by measuring the effects it had on everything around it, and those effects match the presence of matter that doesn't interact with light the way ordinary matter does. Calling it dark matter wasn't an attempt at drama. It was simply the most accurate description available. It is matter. It is dark. And that's nearly all we know with confidence. Still, even with this cloak of invisibility, dark matter shapes galaxies from the inside out. It forms a sort of cosmic scaffolding, a framework that ordinary matter settles into as stars and gas accumulate. Without this unseen structure, galaxies wouldn't form the way they do. Clusters of galaxies wouldn't behave the way they do. The universe wouldn't look the way it does. Dark matter seems to be the gravitational foundation that the visible universe relies on, even if we never directly touch it or see it. That idea alone is strange enough, but the scale makes it stranger still. By current estimates, dark matter accounts for about 85% of all matter in the universe. That means everything we see, every star, planet, nebula, cluster, dust cloud, comet, meteorite, every atom of your body, of the device you're using to listen, of every object you've ever held, makes up a minority portion of what truly exists. The familiar is just a thin layer on top of a far larger hidden structure, and yet all of that is invisible to the senses we evolved with. Knowing this changes the way you imagine the universe. It transforms that sense of emptiness into something more crowded, full of influence, even if lacking in illumination. It's like realizing the stagehands moving props behind the scenes aren't just a few helpers, but a massive unseen group actually determining the entire shape of the performance. The visible actors might get the attention, but they're following cues set by something else entirely. That is the kind of perspective dark matter invites. It doesn't make space feel emptier. It makes it feel loaded with a quiet presence. A presence that doesn't glow, doesn't collide with us, doesn't whisper any signals across electromagnetic waves, but still controls the motion of galaxies wider than our imagination. As scientists kept following this trail, their understanding of the cosmos shifted. What we thought was the main structure of the universe turned out to be just the illuminated decoration on top. If dark matter were somehow removed, galaxies would unravel. Galaxy clusters would scatter. The large-scale patterns of the universe, the filaments and voids mapped by surveys across billions of light years, would fall apart. Dark matter holds the scaffolding together, and this invisible architecture is not spread evenly. It forms patterns, shapes, dense regions that act like gravitational wells, drawing in the gas and dust that eventually become stars and all the familiar objects. So while we can't see it, we can trace its fingerprints through everything that glows. This creates an interesting relationship between visibility and truth. Our eyes evolved to detect light, our instruments amplify that ability, and our intuition rests heavily on the idea that if something is real, we should be able to see it or at least detect it directly. Dark matter challenges that assumption. It sits at the center of a contradiction. We can't perceive it the way we perceive almost everything else, yet it is more abundant and more influential than all the glowing matter combined. Understanding it requires accepting that our senses aren't shaped for cosmic truth, but for surviving on a small planet with trees, weather, and other animals. The universe, as it turns out, contains elements far beyond what biological evolution prepared us for. There's a certain calm in embracing that idea. You don't have to force the universe into being something tidy or familiar. You can simply acknowledge that the cosmos holds features that refuse to fit neatly into everyday experience. Dark matter is one of those. It may not reveal itself in the ways we prefer, but it reveals itself in the ways that matter to the structure of reality. And that makes curiosity about it feel less like an attempt to solve a riddle, and more like trying to understand a partner in a quiet, unspoken dance, one where the visible steps only make sense because of the steady pull of something beneath them. Another layer of this mystery appears when you consider how widespread dark matter must be. It isn't clustered just around galaxies. It forms halos around them, enormous spheres extending far beyond the edges of the starlight. These halos are so large that if you could see them directly, the space around every galaxy would look swollen, with the glowing parts floating inside much larger, heavier structures. When simulations include dark matter, galaxies form naturally. Without it, they simply don't. The math stops working without that extra mass. That suggests dark matter isn't a small correction, it's a dominant component, and its gravitational influence reaches across staggering distances. Thinking about this can make the night sky feel different. Not in a dramatic way, but in a subtle shift of awareness. Instead of seeing stars suspended in emptiness, you can imagine each of them moving through a sea of something you'll never touch. Something that passes through planets and stars without slowing down. Something that exists in abundance yet leaves no visible trace. This can be oddly comforting. Instead of a universe that's harsh and empty, it becomes one that's full in a way we simply haven't evolved to sense. A universe where the true structure is invisible, but dependable. That sense of dependability is what lets us explore the visible part with confidence, knowing that even if most of the matter is dark, the patterns it creates are stable. As we continue drifting into this story, the questions keep unfolding gently. There's no need to push toward the harder details yet, because understanding begins in recognizing the scale of the mystery itself. Dark matter isn't just a placeholder or a mathematical trick. It's a recognition that something real is shaping the cosmos. Something we still don't understand. Something that may eventually reveal itself through particles we haven't discovered or theories we haven't completed. For now, though, the most important thing is knowing that its influence is undeniable. And where that influence shows up, the narrative of dark matter becomes clearer, guiding us toward a deeper look at how this hidden mass helps the universe stay bound together. When astronomers first tried to measure how much mass existed in the universe, they expected the numbers to match the light they could see. It seemed reasonable. If something contains matter, it should give off some kind of signal, whether glowing like a star or shining faintly like scattered dust. The early measurements were done with this assumption in mind. Researchers counted galaxies, tracked how bright they were, analysed the gases between them, and estimated the total mass based on what could be observed. For a while, the results looked straightforward. The visible universe appeared large, but not overwhelmingly so. Everything seemed to scale in a predictable way. Then the data deepened, and the numbers stopped cooperating. The more carefully astronomers looked, the more obvious it became that galaxies were holding together with more strength than the visible matter allowed. Something was pulling on them, adding weight that couldn't be accounted for by stars alone. The notion that the universe seemed too heavy for its own good wasn't an exaggeration. It was a practical observation. When a galaxy spins, the stars near the centre move quickly, and those farther out should move more slowly, following the same principles that apply to objects orbiting a central mass. This is similar to how planets in our solar system orbit the Sun. Mercury travels faster because it's close. Neptune moves slowly because it's far. Gravity dictates that relationship, and for planets, the pattern is clear. But when the same logic was applied to stars within galaxies, the expected slowing didn't happen. The stars in the outer regions moved far faster than they should have, and instead of drifting apart or flying off into space, they remained locked into the galaxy as if tethered by something far heavier than what the telescopes could detect. This observation wasn't a single anomaly. It appeared in galaxy after galaxy. No matter where astronomers looked, the same imbalance showed up. The visible matter wasn't enough to explain the motion. Researchers checked and rechecked their measurements. They recalculated the distances, improved their instruments, and searched for hidden clouds of gas that might account for the missing mass. None of it solved the problem. The numbers consistently pointed to a larger amount of matter than anyone could see. This missing mass didn't seem to behave like ordinary matter. It wasn't clumping in ways that blocked starlight. It wasn't forming nebulae or heating up from collisions. Instead, it appeared to sit quietly in place, influencing motion through gravity alone. One way to picture the imbalance is to imagine placing a handful of visible objects onto a spinning table and watching them behave incorrectly. If the table spins too fast, the objects should slide off, but in galaxies they don't. They stay in place as if something invisible presses them inward. Astronomers needed to understand why this was happening, and the simplest explanation was that the universe contains far more matter than expected. The calculations didn't just show a small mismatch. They revealed that the visible matter accounted for only a fraction of what was necessary to explain the observed motions. The unseen matter had to be several times more abundant. As the evidence accumulated, the term dark matter became the placeholder for whatever this invisible component was. It wasn't meant to sound dramatic, it simply indicated that the matter did not interact with light. That was all anyone could say with certainty. The heavier the universe appeared, the more clear it became that dark matter wasn't just an occasional detail, it was the dominant form of matter. If one could weigh the universe, the visible portion would contribute only a small amount. Everything else would come from something that does not emit, absorb, or reflect light. This shifted the perspective on how galaxies form and how the universe behaves on large scales. The idea that most of the universe's mass is invisible might sound counterintuitive, yet the logic behind it follows ordinary physics. Gravity is a reliable indicator of mass. If objects move too quickly to be held together by the visible mass, then something else must be adding to the gravitational pull, and if the objects stay bound, the extra mass must be considerable. That was the situation astronomers faced. They weren't imagining new laws of physics or inventing exotic explanations. They were simply applying the same gravitational principles that explain falling apples and orbiting planets. When the equations didn't balance, the missing mass became necessary rather than optional. Further evidence came from observing galaxy clusters. These collections of galaxies behave like massive families, interacting through gravity across enormous distances. In the 1930s, measurements of their motion suggested they were moving too fast to remain bound by the visible mass. This raised early suspicions that something was missing, though the tools of the time were limited. Decades later, with better technology and more precise observations, the conclusion resurfaced with greater confidence. Galaxy clusters required far more mass than what was visible. Without it, they would disperse. Instead, they stayed together, implying the presence of a significant gravitational force exerted by something unseen. Light itself provided another clue. When light from distant galaxies passes through clusters, it bends due to gravity, a phenomenon called gravitational lensing. The degree of bending can be measured, and the amount of mass required to cause that bending can be calculated. When scientists performed these calculations, they consistently found more mass than the visible components could supply. This independent method reinforced the earlier findings. It didn't rely on the motion of stars or galaxies. It relied solely on the deflection of light. Once again, the mass detected exceeded what could be seen. These mismatches pointed toward a larger reality, one in which the visible universe was only a surface layer floating on a deeper, heavier foundation. This weight of the unseen didn't simply press galaxies together. It shaped their formation from the earliest periods of cosmic history. Numerical simulations helped illustrate this. When models included only visible matter, galaxies struggled to form naturally. The distribution didn't match what telescopes observed. But when the models included a background of dark matter, galaxies assembled in stable, recognizable ways. The invisible mass provided a framework that guided the visible matter into its familiar structures. This wasn't a minor detail, it was essential. Without the unseen mass, the universe wouldn't resemble the one we see. Stars wouldn't cluster in the same patterns. Large-scale structures wouldn't form the intricate web-like distribution mapped by modern surveys. It became clear that the universe doesn't merely appear heavier than expected. It fundamentally is heavier. The visible matter is only a thin slice of a much larger whole. The implications of this reach into every corner of cosmology. The rate at which galaxies merge, the distribution of clusters, the background radiation left from the early universe, all point to a cosmos shaped by mass that doesn't respond to light. This quietly influences everything while remaining outside ordinary detection. It moves through us, through planets, through stars, without resistance. It doesn't warm up or cool down from collisions. It simply persists while exerting gravitational force. The conclusion that the universe carries far more mass than expected raised new questions. What is this unseen substance made of? Why does it not interact the way familiar matter does? Does it consist of particles, Does it come from a modification of existing physical laws? These questions didn't have immediate answers, but they offered a direction for further investigation. The first step was simply acknowledging the scale of the problem. Before considering exotic explanations, the numbers had to be accepted. And the numbers showed quite plainly that the universe's visible content doesn't come close to accounting for its gravitational behaviour. Something else is present. This mismatch between what we observe and what gravity demands isn't something that can be resolved by adjusting a few equations. The magnitude of the discrepancy is too large. The additional mass needed to explain the observations isn't a small correction. It is several times larger than the total visible mass. That's why the notion of dark matter took hold. It wasn't an attempt to invent a new substance out of nowhere. It was a recognition that the universe refuses to behave as if only visible matter exists. Considering this, the idea of the universe being too heavy becomes less of a surprise and more of a starting point. The imbalance in mass isn't a flaw in the observations, it's a clue about the true composition of the cosmos. Accepting that the largest part is unseen allows researchers to focus on what shapes this hidden mass might take. Although the details remain uncertain, the broader picture is consistent. The gravitational effects show up at every scale where they can be measured. They show up in galaxies, in clusters, in the bending of light, in the temperature distribution of the cosmic microwave background, and in simulations attempting to recreate the large-scale universe. Whenever a new method is used to weigh the universe, the same conclusion appears. The visible components don't add up to the observed gravitational pull. No matter how many stars are counted or how deeply dust clouds are measured, the extra mass continues to emerge as a requirement. This consistency across multiple lines of evidence strengthens the case that dark matter is not an invention, but a genuine component. Not seeing it doesn't reduce its importance. Some parts of the universe influence events through interactions we can't sense directly, and dark matter seems to be one of those parts. The idea that the universe is loaded with more weight than expected also shifts how we think about the cosmic environment we live in. Instead of floating through empty space, Earth moves through a region filled with unseen matter. This doesn't mean there is a danger or that dark matter affects us in any noticeable way. It simply means that our surroundings are more complex than what our senses can detect. The gravitational landscape is shaped by both the visible and invisible components, and the motions of stars and galaxies reflect that combined influence. The realization that something unseen was adding so much weight to the universe naturally led researchers to think about how this hidden mass affects the structures we can observe. When galaxies were first studied closely, they didn't behave like simple mechanical systems. Instead, they acted as though surrounded and supported by something holding them together, more strongly than the stars alone could manage. It was as if an invisible glue wrapped around every galaxy, pulling its outer stars inward with a force that shouldn't have been there if only the visible matter were responsible. This glue-like behaviour wasn't a metaphor researchers used lightly. It emerged from straightforward measurements that refused to align with expectations. A galaxy isn't a rigid object. It's a collection of stars, gas, dust, and other visible material all moving under the influence of gravity. Some parts rotate more quickly than others, but the overall pattern should follow the principles seen in other systems bound by gravity. When that didn't happen, the obvious question became what was missing. If stars are moving too quickly to stay bound by the visible mass, then something else must be contributing. Otherwise, those stars would drift away and the galaxies wouldn't last long on cosmic timescales. Yet galaxies do last. They remain stable across billions of years. So the missing stabilizing force couldn't be small, it had to be substantial. Through continued measurements came the picture of galaxies surrounded by enormous halos of unseen matter. These halos didn't glow and didn't appear in optical images, but their presence was inferred from the way they influenced motion. When researchers modelled galaxy behaviour, they found the visible portion acted like a central region, embedded in a much larger pool of mass. The halo extended far beyond where the last star was visible, spreading out into the dark with no clear boundary. The stars orbiting at the edges weren't being held by the visible material of the galaxy. They were being held by this invisible halo that contributed most of the mass. This invisible glue wasn't sticky in the traditional sense. It didn't work by contact or friction. It worked through gravitational influence. If something has mass, it can attract other things with mass, and if enough mass is present, the resulting gravitational field can be extremely strong even if the material isn't visible. This was the case with dark matter. It didn't scatter light or form bright structures, but it created a gravitational landscape that shaped the entire galaxy. The stars followed that landscape, moving along paths determined by a mass they couldn't collide with or interact with directly. That made dark matter an unusual type of glue, one that bound galaxies without ever touching them in the ways ordinary matter does. The existence of these halos became clearer when astronomers compared different kinds of galaxies. Large spiral galaxies like our own had rotation curves that flattened instead of dropping off. Smaller galaxies showed similar behavior, sometimes even more extreme. In some dwarf galaxies, the visible matter was too little to hold anything together at all if dark matter were absent. Yet the galaxies existed. They didn't dissolve. They rotated with surprising stability. The only explanation was that dark matter must be providing most of the gravitational pull. This was consistent across many types of galaxies, not just a few unusual cases. Gravitational lensing provided further evidence of this glue-like presence. When light from distant objects passes near a galaxy, the path bends due to the galaxy's mass. By measuring how much the light bends, astronomers can estimate how much mass must be present. In many cases, the bending was far greater than expected from visible matter alone. This meant the galaxies were heavier than they looked. Their mass extended beyond what the eye could see, indicating once again the presence of dark matter halos. These halos were not just large, they dominated the total mass distribution. The visible parts of galaxies were embedded in them like small glowing regions within much larger invisible structures. The concept of an invisible glue became more meaningful when researchers studied galaxy collisions. When galaxies pass through each other, the stars rarely collide, but the gas clouds do. They slow, heat up, and sometimes form shock waves. However, gravitational lensing showed that most of the total mass in such collisions moved straight through without slowing. The mass didn't match the distribution of the gas. Instead, it followed the stars, which should not have been possible if the extra mass were part of the gas itself. This indicated the unseen mass didn't interact with gas or with itself in ways that would cause friction. It moved cleanly through the colliding galaxies, still providing gravitational influence but not participating in the collision. That behaviour suggested dark matter isn't just invisible, it's also non-reactive in almost every way except gravity. This came into clearer focus in observations of a system known as the Bullet Cluster. Two galaxy clusters had collided, and the gas from each cluster had interacted strongly, slowing and heating. But the gravitational lensing showed most of the mass had passed through unimpeded, separating from the visible gas. That result aligned perfectly with the dark matter model. The invisible component didn't collide, it didn't compress, it simply moved through while continuing to exert gravitational influence. This provided strong evidence that the invisible glue holding galaxies together wasn't made of normal matter hidden from view. It had properties that required it to be something fundamentally different. Understanding this invisible glue reshaped ideas about how galaxies form. Before dark matter was widely accepted, the process seemed difficult to model accurately. If the early universe contained only visible matter, gas clumps wouldn't gather quickly enough to form galaxies in the time available. The observed structures required additional gravitational pull, and dark matter provided it. Simulations showed that when dark matter was included, it formed dense regions early on. These regions acted as seeds around which gas could accumulate. Over millions of years, the gas cooled and formed stars, creating the galaxies we see today. Without the dark matter seeds, the universe's structure would not match observations. Thinking of dark matter as invisible glue helps illustrate its role in stabilizing and shaping galaxies. But it's also important to recognize that this glue doesn't behave like anything familiar. It doesn't clump into small objects the way visible matter does. Instead, it forms smooth halos. It doesn't gather into disks. It doesn't collapse into stars. It prevents galaxies from tearing apart, but it doesn't contribute to their visible features. It creates the framework, not the details. This separation of roles is unique. Ordinary matter handles the glowing parts. Dark matter manages the gravitational stability. The glue-like behavior also appears in galaxy clusters, where dark matter acts as the dominant binding agent. These clusters are enormous, containing hundreds or thousands of galaxies. The visible matter inside them behaves almost like decoration compared to the mass contributed by dark matter. The galaxies orbit the cluster's center, held in place by a gravitational field mainly shaped by unseen material. Without dark matter, the clusters would not remain intact. They would expand and disperse. Instead, they stay bound, showing once again that something holds them together beyond the visible. The more astronomers learned about this invisible glue, the more questions emerged about its true nature. It wasn't enough to know that it held galaxies together. Researchers wanted to know what it actually was. Several ideas were explored, ranging from undiscovered particles to modifications of gravity. But before considering those, the evidence for dark matter's influence had to be solid, and it became clear through repeated observations that the simplest explanation remained the most consistent. Something unseen exerted gravitational force in a way that ordinary matter could not account for. The behavior of the invisible glue also showed up when studying the motion of stars within spherical systems. These systems don't have the visible structure of a spiral galaxy. They're more diffuse. Yet even there, the stars moved as though surrounded by a large reservoir of mass. The farther out one looked, the stronger the need for dark matter became. These patterns weren't random. They followed predictable trends that matched a mass distribution extending beyond the visible boundaries. In addition, the invisible glue's presence explained why some galaxies could be so faint yet remain intact. Ultra-diffuse galaxies have very few stars, making them difficult to detect. But the stars inside move as though they're backed by enormous halos of dark matter. If the visible stars were all that existed, these galaxies wouldn't be able to hold themselves together. Yet they do. This provides another line of reasoning that points toward dark matter's stabilizing role. Across all these observations, the pattern emerges that galaxies are not held together solely by the matter we can see. Their stability depends on a broad, unseen component. This discovery wasn't a single leap. It was a gradual accumulation of evidence that pointed in the same direction. Even with this understanding, there remains a sense of curiosity about what this invisible glue is made of. Although researchers haven't reached a final explanation, the consistency of the gravitational evidence is difficult to ignore. Reflecting on these ideas, the universe becomes easier to imagine not as a place held together by the familiar, but as a structure shaped mostly by the unseen. Stars create patterns that we admire, but they trace paths determined by a background of invisible mass. The glue doesn't announce itself, it doesn't shine or make noise. It simply provides the gravitational structure that allows galaxies to exist in their current form. The recognition that something important was missing from the universe didn't begin with modern technology or advanced simulations. It started with straightforward observations made long before dark matter became a widely discussed idea. Early astronomers who examined the motions of galaxies and clusters weren't searching for invisible mass. They were simply measuring how objects moved through space. They expected the behavior to follow the known rules of gravity, and when the data refused to match those rules, the situation grew puzzling in ways that couldn't be dismissed as simple mistakes. These first signs didn't immediately point to a new form of matter. They appeared instead as small irregularities that suggested something wasn't adding up. One of the earliest clues came from a study of galaxy clusters in the 1930s. At that time, measuring distances and velocities was difficult, and the tools available were far less precise than what we have today. Even so, the motions of galaxies within certain clusters raised questions. A Swiss astronomer studying these clusters attempted to calculate the total mass based on the speeds at which the galaxies were moving. His reasoning was direct. If galaxies inside a cluster are moving quickly, the cluster must contain enough mass to keep them gravitationally bound. Otherwise, they would disperse over time. When he performed the calculations, the mass required to keep the cluster intact far exceeded the mass visible through telescopes. The discrepancy wasn't small, it was several times larger than expected. This result wasn't embraced immediately. The scientific community viewed it as unusual, and possibly the result of measurement errors. Instruments had limitations, and early distance estimates could easily be off. The idea that the universe contained large amounts of unseen matter felt speculative at the time. Many researchers assumed the results would eventually align with visible matter once better data arrived. For a while, that approach seemed reasonable. Astronomers continued gathering information, expecting the mismatch to shrink as observations improved. However, the inconsistency didn't fade. It appeared again when scientists examined the rotation of galaxies. These studies gained momentum decades later. Once more accurate tools made it possible to measure how stars moved around the centers of galaxies. Researchers observed that stars farther from the center were moving much faster than expected. According to classical gravitational principles, those outer stars should have been slower. The visible mass at the center of the galaxy wasn't enough to hold them in place. If only the visible stars and gas were present, the galaxies should have been unstable. Yet the galaxies remained intact, their stars moving in stable orbits that shouldn't have been possible with only the matter astronomers could see. This wasn't a fringe observation. It was consistent across many galaxies. Spiral galaxies in particular showed rotation patterns that flattened rather than tapering off with distance from the center. The more data astronomers collected, the more the pattern repeated. The outer regions behaved as if submerged in an enormous, invisible mass. This realization didn't come from a single measurement. It emerged from a growing body of evidence that refused to fit the expected gravitational pattern. The discrepancy became difficult to ignore. Even if early cluster measurements were uncertain, the galaxy rotation curves were too clear to dismiss. As researchers continued to compare the expected behavior of galaxies with the actual behavior, they had to consider explanations that went beyond miscalculations. The mismatch persisted in various contexts. Light measurements couldn't account for the necessary mass. Infrared surveys didn't uncover enough cold matter to fill the gap. Attempts to explain the missing mass through faint stars, dense clouds, or other hard-to-see forms of ordinary matter didn't work. None of the visible or easily hidden components provided the amount of mass needed to stabilize galaxies and clusters. The more thorough the search, the more obvious it became that ordinary matter alone couldn't explain the universe's structure. In addition to rotation curves and cluster dynamics, other forms of evidence appeared gradually. When astronomers used gravitational lensing to map mass distributions in clusters, they saw that the bending of light indicated far more mass than the luminous matter provided. This lensing didn't rely on the brightness of objects, but on how mass distorted the path of light from background galaxies. Since the degree of bending depends on total mass, the lensing maps offered another independent way to weigh structures. Over and over, these maps showed mass concentrations that didn't align with the visible components. It became difficult to imagine that all of this unseen mass could be explained by conventional objects that simply happened to escape detection. Even earlier in cosmic history, the distribution of temperature variations in the cosmic microwave background revealed something unusual. When scientists measured the faint fluctuations in this background radiation, they found patterns that reflected the density variations present shortly after the universe began. These patterns provided a record of how matter was arranged in that early era. Analysis showed that visible matter alone couldn't produce those patterns. The universe appeared to contain a significant amount of mass that didn't interact with radiation. pointing again towards something beyond ordinary matter. As evidence accumulated across different observational methods, the picture became increasingly clear. The missing mass wasn't a small part of the universe, it was the majority of it. This conclusion came from unrelated lines of inquiry, each reinforcing the others. No matter how the universe was weighed, gravity consistently pointed toward an unseen component. This growing recognition didn't solve the mystery, but established the need to look for something that didn't interact with light while still possessing mass. The concept of dark matter developed from this recognition, not as a guess, but as a necessary explanation for a wide range of phenomena. The early researchers who encountered these inconsistencies didn't immediately declare that a new form of matter existed. Instead, they proposed possibilities, tested alternatives, and gradually ruled out explanations that didn't fit the data. The missing component had to be something that contributed to gravity without interacting through electromagnetism. That excluded most familiar forms of matter. It meant this component wouldn't emit light, absorb it, or reflect it. It wouldn't form bright structures, wouldn't collapse into stars, and wouldn't reveal itself through typical observational channels. The only reliable indicator of its presence was gravitational influence. This recognition shaped a new way of studying the universe. Rather than relying exclusively on visible structures, astronomers began tracing cosmic behavior to reveal what couldn't be seen directly. Motion became a tool for detecting mass. Light bending became a way to map invisible matter. Temperature variations in the cosmic background became clues about early mass distribution. Each method pointed toward the same conclusion. Something was missing from the visible count, and whatever it was, it dominated the mass budget of the universe. The shift in perspective didn't happen suddenly. It developed gradually as repeated attempts to match visible matter with observed motion failed. Researchers had to accept that the universe couldn't be described accurately based on light alone. This meant that telescopes, no matter how powerful, would only reveal a portion of what existed. Instruments that measured mass indirectly became just as important as those that captured images. As the idea gained traction, theoretical physicists considered what forms this unseen matter might take. They began exploring models that allowed for matter with mass but without electromagnetic interactions. This step didn't provide immediate answers but opened new pathways for research. Understanding what was missing required both observational and theoretical work, and the two informed each other. The process wasn't about proving a single idea, but about excluding alternatives that didn't explain the combination of galaxy rotation, cluster behavior, lensing results, and cosmic background patterns. While the realization that something substantial was missing continued developing, the effort to match the missing mass with ordinary matter reached a limit. Astronomers searched for collections of dim stars, small planets, and cold gas clouds. These possibilities felt practical at first, since faint objects might be hard to see. But as surveys broadened and covered wider ranges of wavelengths, these potential sources failed to appear in sufficient quantities. They couldn't account for a fraction of the missing mass, let alone the majority. The invisible component had to be different in a fundamental way. The notion that most mass in the universe might be invisible challenged assumptions about how matter behaves. It implied that familiar forms of matter aren't the default or primary components. Instead, the dominant form might be something entirely separate. This shifted the focus of research from cataloguing visible structures to understanding how invisible mass shapes the universe's evolution. The recognition that something was missing therefore became the starting point for a much larger effort, one that would continue through studies of structure formation, particle physics, and cosmology. The decision to call this missing mass dark matter wasn't meant to provide an answer. It served as a placeholder for an idea that demanded further exploration. The term simply acknowledged that the matter didn't interact with light. As observations continued, the need for such a placeholder became essential. The evidence pointed toward a universe structured by a component that refused to show itself directly, but made its presence known through gravitational effects. Gradually, the community moved from questioning whether something was missing to accepting that the universe couldn't be understood without including this hidden component. The gap between observations and theoretical expectations grew too large to ignore. Recognizing that something was missing wasn't the end of the problem. It was the beginning of trying to understand why the missing mass existed and how it shaped everything from galaxies to the largest structures in the cosmos. When astronomers began looking closely at how stars moved through their galaxies, they didn't expect anything unusual. The motion of stars should have followed the same general principle seen everywhere else gravity has a role. Something with more mass pulls more strongly. Something farther away feels less pull. These ideas were familiar and trustworthy, supported by centuries of work. So the early measurements of stellar motions inside galaxies seemed like they would confirm what was already known. Instead, the numbers revealed an inconsistency large enough that it forced a reconsideration of basic expectations. The stars weren't behaving as they should have if only visible matter were influencing them. Their paths suggested a hidden weight holding everything together more tightly than expected. When a star orbits the center of a galaxy, its motion depends on the total amount of mass enclosed within its orbit. Stars near the center have a lot of visible mass inside their path. They move faster, which lines up with expectations. Stars farther out have much less visible mass enclosed. They should move more slowly, the same way planets far from the Sun move more slowly than those close to it. The expectations seemed reasonable, but when astronomers actually measured the speeds of stars at different distances from the galactic center, the pattern didn't match. The stars in the outskirts weren't slowing down. They were moving at nearly the same speed as the stars closer in. This didn't agree with the gravitational pull that visible matter alone should provide. The situation grew more interesting as more data came in. It didn't matter which galaxy researchers looked at. The pattern repeated itself. The outer stars coasted along with an unexpected steadiness, often at speeds that should have sent them drifting off into intergalactic space. Yet they remained bound, circling the galaxy as though held by something large and unseen. This suggested that the mass responsible for stabilizing the galaxy wasn't concentrated only where the light was. It had to extend much farther out, enveloping the galaxy in a broad region of unseen matter. The stars were responding to gravity, but the source of most of that gravity wasn't visible. To illustrate how surprising this was, consider how the solar system works. The Sun contains nearly all of the solar system's mass. The planets orbit at speeds determined by the Sun's gravitational pull. As you move farther out, the pull becomes weaker, and the orbital speed decreases. This is predictable and matches observations. If the planets suddenly began moving faster than the Sun's mass could account for, we would immediately recognize that something extra was influencing them. That is essentially what galaxies revealed. The stars behaved as though the majority of the mass wasn't at the center, but spread through a large invisible halo. Some astronomers initially wondered whether the visible mass had been underestimated. Maybe there were faint stars that couldn't be detected easily, or large amounts of cold gas that didn't emit much light. Perhaps dust clouds blocked parts of galaxies from view. These ideas were reasonable to consider, but they didn't solve the problem. Even when accounting for hidden gas, faint stars and dust, there still wasn't nearly enough mass to explain the motions. The required mass exceeded what any form of ordinary matter could supply. The outer stars continued moving too fast to be held by visible matter alone. As the evidence grew, the idea solidified that galaxies were embedded in massive halos of unseen material. These halos did not appear in images because they didn't interact with light. The stars at the edges moved quickly, not because something was wrong with gravitational theory, but because they were responding to a gravitational field shaped by this unseen mass. The more astronomers mapped these rotation curves, the more they had to accept that most of the mass in a galaxy wasn't visible. The stars were whispering this information through their motion, orbit after orbit, showing that galaxies could not exist in a stable form without a major unseen component. The consistency of the effect made it compelling. Spiral galaxies showed it clearly with their flattened rotation curves. Elliptical galaxies, although more difficult to measure, also hinted at the presence of large amounts of unseen mass. Dwarf galaxies presented an even stronger case. Some of them contained very few stars, yet the stars they did have moved quickly enough to suggest halos far more massive than the visible components. This implied that dark matter wasn't an occasional feature of certain galaxies. It appeared to be a universal feature, present wherever gravitational measurements could be made. Another curious detail emerged when comparing the mass distribution of galaxies to their visible structure. In many cases, the visible matter alone was not arranged in a way that could create the observed gravitational field. For example, if the mass were only located in the bright central regions, the outer stars would still need to slow down as distance increased. They did not. The gravitational influence had to extend outward, surrounding the galaxy like a broad shell. This invisible structure shaped the motions in a way that couldn't be duplicated by rearranging the visible components. It didn't matter how astronomers redistributed the light or refined the measurements. The pattern persisted. The stars at the outskirts weren't just moving too quickly. They were moving in a manner that suggested the unseen mass had a specific distribution. The simplest explanation was that this mass formed a roughly spherical halo. It didn't collapse into a disk the way visible matter did. It didn't form stars or planets. It remained spread out, reaching far beyond the luminous regions. The galaxies themselves appeared as embedded structures inside this much larger gravitational container. The stars were responding to this container, not only to the material they could see. It's helpful to picture this through an analogy, though the actual dynamics are more complex. Imagine a small lit-up object placed inside a much larger dark sphere. If the sphere is massive enough, anything moving inside it will respond to that mass even if the sphere itself remains invisible. The lit-up object might appear to be the only matter, but the motions inside would reveal the sphere's presence. That's similar to what galaxies demonstrate. Their stars give away the existence of the halo through their motion. The halo remains unseen in images, but its gravitational effect is unmistakable. As this idea took hold, astronomers began incorporating it into simulations of galaxy formation. When only visible matter was included, the galaxies that formed didn't match what telescopes saw. They were too small, too fragile, and lacked the extended shapes observed in the universe. When dark matter halos were added, the galaxies formed more naturally. They developed stable structures, maintained their shapes, and produced rotation curves similar to what astronomers observed. This showed that dark matter wasn't just a theoretical fix for an observational problem. It was necessary for explaining how galaxies come to exist and remain stable. The mystery deepened as researchers tried to determine what dark matter might be made of. But long before diving into particle candidates or alternative theories, the stars had already presented the key observation. They were moving too fast to be held by visible matter. Their motions were measured repeatedly in different galaxies, using different instruments and under different conditions. The results were consistent. The stars were not behaving incorrectly. They were behaving in a way that made complete sense if most of the galaxy's mass was invisible. The mystery, they whispered, was simply that the universe contained much more than anyone had realized. One of the most striking examples of this behavior appeared in galaxies known as low-surface brightness galaxies. These galaxies have very little visible light, yet the stars they contain move at speeds similar to those in much brighter galaxies. This shouldn't be possible if ordinary matter were the only contributor. These galaxies should barely hold together. Yet their rotation curves remained flat, indicating strong gravitational support from something not seen in the faint starlight. This provided another compelling point. The invisible mass was not tied to visible brightness. A galaxy could glow intensely or barely at all, and still be dominated by a dark halo. Studies of gas in galaxies added another layer of information. Gas often extends farther out than the bright stars, and by tracking the motion of this gas, astronomers could trace the gravitational field even farther. The pattern continued. Even in regions where there were few, if any, stars, the gas moved at speeds that required additional mass. These measurements reinforced the idea that dark matter halos were widespread and that they shaped the motions of objects far beyond the visible limits of galaxies. Another observation came from the comparison of galaxy types. Some galaxies contain dense central bulges, while others are more diffuse. Despite these differences, the rotation curves often shared the same flattening behaviour. This consistency suggested that the unseen mass wasn't tied to the luminous structure. It surrounded the entire galaxy in a way that didn't depend on the precise arrangement of stars. The stars were simply reacting to the underlying gravitational landscape created by the halo. The mystery whispered by the stars wasn't limited to individual galaxies. When astronomers examined entire groups of galaxies, they found that these systems also moved in ways that implied large amounts of unseen mass. The galaxies were pulled together more tightly than visible matter allowed. Their motions reflected a deeper gravitational well. This meant that dark matter wasn't only present in individual galaxies, it extended to much larger scales. The stars, through their orbits, provided one of the clearest signals that something fundamental was missing from the visible matter count. They revealed the structure of their gravitational environment without needing to interact with anything directly. Their motion acted as a natural probe, sensitive to the mass distribution around them, and because stars behave reliably under the influence of gravity, their observed speeds could be trusted. They weren't fluctuating randomly. They followed stable orbits that reflected the mass present in the galaxy. Even when astronomers examined galaxies at different stages of their evolution, the same pattern emerged. Early galaxies forming in the young universe showed signs of rapid rotation and mass distributions that required dark matter. This indicated that dark matter had been influencing the universe from early times, shaping the development of galaxies before they fully formed. The stars were part of a larger structure influenced by unseen mass long before the universe reached its current state. The growing body of observations made it clear that dark matter wasn't a minor component added to refine models. It was central to understanding why stars move the way they do. Their motions were clues placed everywhere in the sky, pointing toward a universe whose structure depended heavily on something invisible. These clues weren't vague. They were measurable, repeatable, and consistent. They came from galaxies large and small, from nearby systems and distant ones, from gas clouds and star clusters. Every line of evidence supported the same conclusion. As more information accumulated, astronomers didn't simply observe the mystery. They continued using the stellar motions to map the invisible halos, building clearer pictures of how dark matter might be distributed. These maps revealed structures extending far beyond the regions where stars were visible. They showed how the unseen mass varied in density, how it supported the galaxy, and how it influenced the motions within. The stars didn't solve the mystery of what dark matter is, but they made it impossible to deny that it exists. The more astronomers followed the strange motions of stars, the more it became clear that gravity alone, at least as produced by visible matter, wasn't sufficient to explain what the universe was doing. Gravity was behaving exactly as expected, yet the results didn't match the matter that could be observed. This wasn't gravity acting incorrectly. It was gravity responding to something else, something that wasn't being accounted for. The realization grew that gravity had a partner contributing to the overall pull, one that couldn't be detected directly, one that left no light and made no sound but still shaped the motion of galaxies with remarkable consistency. This hidden partner was inferred through its influence, not through direct interaction, and understanding its nature became a central pursuit in astronomy. When an object moves under the influence of gravity, the motion provides a measurement of how much mass affects it. This principle is reliable across countless applications. It guided early work on planetary motion and helped establish how stars and galaxies should behave. If gravity pulled harder than expected, something had to be causing that extra pull. If things stayed bound when they shouldn't have, there had to be additional mass somewhere. These statements weren't speculative. They were rooted in the same gravitational laws that describe falling objects on Earth. The stars, galaxies, and clusters weren't bending those rules. They were following them precisely. That meant the missing component wasn't a failure of gravity, but a sign that something else was present. This hidden influence became clearer when astronomers compared the amount of visible matter inside galaxies with the gravitational strength needed to hold them together. The difference was not small. The visible material accounted for only a fraction of what the galaxy required. The outer stars moved at speeds that demanded more mass, and even the inner regions showed gravitational fields that didn't match their light-based mass estimates. When these calculations were extended to larger structures, the gap widened further. Galaxy clusters required enormous amounts of mass to keep individual galaxies bound to the cluster. Without the unseen contribution, the clusters should have dispersed long ago. Yet they remained stable, moving in patterns that indicated gravitational fields far stronger than anything visible. These observations pointed toward a partner to gravity, though partner here meant something participating in gravity rather than altering its fundamental nature. Gravity acts on mass, and the missing contribution implied that most of the mass was invisible. That invisible mass was the source of gravity's extra strength. It didn't change gravity itself. It changed what gravity had to work with. This distinction shaped the way astronomers understood the problem. The fundamental laws weren't broken. The inventory of matter was incomplete. This partner force wasn't a new fundamental interaction. Instead, it was mass that gravity responded to as it always does. The strength of this idea grew as gravitational lensing revealed mass distributions in distant clusters. Light bending around massive objects provided a way to map the mass independent of visible brightness. When these lensing maps were compared to optical images, they didn't match. The regions of strongest bending often didn't align with the brightest objects. The mass distribution was wider and heavier than the luminous material suggested. This reinforced the notion that gravity was tracing something hidden. The light failed to reveal it, but gravity couldn't ignore it. By following the bending of light, astronomers traced the invisible mass, outlining structures that didn't glow yet accounted for most of the gravitational effect in the region. This mismatch made it clear that the unseen component wasn't just a minor correction, it was dominant. Visible matter contributed only a small portion of the total mass influencing gravitational behaviour. The hidden partner was far more abundant, shaping galaxies and clusters in ways that the visible fraction couldn't. Even when astronomers tried using the most generous estimates of faint stars or dim gas clouds, the missing mass remained overwhelmingly large. The partner had to be distinct. It couldn't simply be ordinary matter hidden from view. It didn't emit radiation, didn't absorb it, and didn't reflect it. Something that dark but so massive needed to behave differently from the matter familiar to us. Another clue emerged from studies of how galaxies formed in the early universe. Visible matter alone couldn't clump quickly enough to form galaxies within the observed timeframes. It was too affected by radiation in the early universe to gather efficiently. Something unaffected by radiation had to begin forming structures earlier, providing gravitational wells into which visible matter could later fall. This implied the hidden partner was already shaping the universe when the first visible stars formed. It didn't interact with radiation, allowing it to collapse under gravity long before ordinary matter could. This early formation helped explain why galaxies developed the way they did. The visible structures were building on a framework established by something dark and abundant. If visible matter were the only contributor, galaxies wouldn't resemble the ones observed today. They would be smaller, less stable, and distributed differently across the universe. Large-scale structures such as cosmic filaments and voids wouldn't have the patterns surveys reveal. When researchers simulated the universe using visible matter alone, the results didn't match the cosmic web. But when they included the hidden partner, the structures aligned with observations. The partner mass created deeper gravitational wells that allowed matter to gather and form the observed arrangement. The agreement between simulations and observations strengthened the conclusion that this invisible component played a critical role from the earliest moments of galaxy formation. Because the hidden partner doesn't interact with light, astronomers rely on gravity to detect it. This method isn't new. It's the same principle used historically to discover new celestial bodies. Neptune, for example, was inferred before it was seen. Its gravitational influence altered the motion of Uranus, leading astronomers to predict its existence. They calculated where Neptune should be and later confirmed its presence. The hidden partner of gravity is a more extreme version of that logic. The influence is widespread, affecting countless structures. Unlike Neptune, which could eventually be seen, this partner remains invisible to all light-based detection methods. But the principle remains similar. Gravity reveals objects regardless of visibility. In some cases, stars at the edges of galaxies behaved as though the galaxy's mass was nearly 10 times greater than what starlight indicated. This revealed that visible matter could not be the full story. The stars, gas and dust accounted for a small fraction of the total. More mass was needed to explain why galaxies didn't fall apart. This discrepancy wasn't isolated. It appeared in nearly every galaxy where rotation curves were measured. The missing mass had to be a fundamental feature of galaxies, not a rare occurrence. Since the partner could not be observed directly, astronomers turned to particle physics for possible explanations. The mass had to come from something with gravitational influence but without electromagnetic interaction. This meant it wouldn't absorb or emit photons. It wouldn't behave like atoms or molecules. It wouldn't participate in chemical reactions or form complex structures. Instead, it would exist primarily as a gravitational source. This narrowed the range of possibilities. The partner might be a particle with mass, but without electric charge. Or it could be a collection of such particles that don't form the bonds familiar to ordinary matter. Alternative ideas were also considered, including modifications to the laws of gravity. If gravity acted differently on large scales, perhaps the missing mass wasn't required. But these modifications had difficulty explaining the full range of observations. They could sometimes match galaxy rotation curves, but struggled with galaxy clusters or cosmic microwave background data. They also failed to reproduce the lensing effects in merging clusters, where the mass distribution clearly separated from the visible gas. These difficulties pushed the focus back toward the existence of unseen mass rather than altered gravitational laws. The hidden partner doesn't clump like ordinary matter. It doesn't collapse into stars or form disks. Instead, it spreads into halos, maintaining a smooth distribution around galaxies. This distribution explains why the rotational behavior remains consistent across different types of galaxies. The visible structure may vary, but the halo shapes the overall gravitational environment. As a result, stars follow paths dictated by the halo's mass distribution, which extends far beyond the luminous boundaries. Even though the hidden partner cannot be seen, it behaves predictably through gravity. This predictability allows astronomers to map it indirectly. By tracking the motions of stars, gas and galaxies, researchers can determine where the invisible mass must be. These maps show that the partner component is everywhere, supporting structures across the universe. It fills galaxy halos, permeates clusters, and contributes to the cosmic web. Even though it doesn't reveal itself through conventional means, its gravitational presence is unmistakable. The partner's consistency across different systems suggests it is a major component of the universe rather than a minor addition. This shapes how cosmologists interpret countless observations. The expansion rate of the universe, the clustering of galaxies, and the temperature fluctuations in the cosmic microwave background all depend on the amount of mass present. Without the hidden partner, the universe's behavior wouldn't match measurements. Including it produces results that align with what telescopes observe. Since gravity responds to all mass equally, the partner influences matter regardless of its type. Visible and invisible components both contribute to the gravitational field, shaping motion at every scale. This connection links small systems such as dwarf galaxies to vast clusters and large-scale structures. The partner mass plays a role in all of them. Because the partner cannot be observed through direct interaction, inferring its nature remains an active area of research. Various detection methods aim to catch a glimpse through subtle effects or rare interactions, but no confirmed detection has been made yet. Despite this, the gravitational evidence is overwhelming. The universe behaves as though it contains far more mass than what can be seen. This partner influences galaxies consistently, making it an essential part of the cosmic landscape. The idea of gravity having such a partner highlights the limitations of relying solely on what can be seen. The universe isn't structured according to visibility. It's structured according to mass, whether visible or not. This shapes the way astronomers think about observation. Light reveals only part of the picture. Gravity reveals the rest. As astronomers became increasingly aware that the visible universe could not account for the gravitational behavior they measured, they needed ways to trace the presence of the unseen component. Since it didn't emit light or absorb it, the usual observational tools couldn't reveal where it was concentrated. Instead, researchers had to rely on indirect methods, building maps of galaxies and clusters, not from light alone, but from the gravitational effects on anything that passed through or moved within those regions. These maps gradually formed a picture of mass distributions that didn't match the luminous patterns. What appeared to be empty space often contained significant amounts of mass, while regions with bright clusters sometimes held far less unseen material than expected. This demonstrated that the arrangement of mass in the universe didn't follow the light in a simple way. The visible parts were not accurate indicators of the underlying gravitational landscape. The simplest way to begin mapping the invisible was to examine how stars moved. By measuring the speeds of stars at various points within a galaxy, astronomers could infer how much mass must be inside their orbit. If stars moved too fast for the visible mass to hold them, the extra mass had to be added to the map, even if nothing could be seen there. When enough measurements were taken at many distances and angles, a pattern emerged. The visible disk of stars represented only a fraction of the mass, while the invisible component formed a wide halo reaching far beyond the regions where starlight faded. These early maps were rough, built from limited data, yet they revealed a consistent trend. The unseen mass was not only present, it dominated the structure, controlling the behavior of the galaxy more than the luminous portion. As technology advanced, the mapping methods became more refined. Radio observations helped measure the motion of hydrogen gas, which extended farther than stars and provided additional insight into the gravitational field. The gas moved in ways that showed the same flattening of rotation curves seen in stars. This reinforced the idea that the halo wasn't confined to areas where stars were present. It stretched well beyond them, remaining the dominant component of the galaxy's mass. By combining stellar data and gas data, astronomers began constructing broader maps of mass distribution. These maps showed halos enveloping galaxies like enormous shells, with densities gradually decreasing outward, but extending far enough to influence regions where no visible matter could be found. Although these rotation-based maps were important, they didn't give a complete view. They relied on material inside the galaxy itself, and couldn't reveal structures in empty-looking regions or interactions between galaxies. Researchers needed tools that could trace mass, even when no stars or gas existed. They turned to gravitational lensing, a method based on how mass bends light passing near it. Light travelling through the universe doesn't move in perfectly straight lines when massive objects lie in the path. Instead, it curves slightly, depending on the mass. This effect allowed astronomers to measure the mass distribution in a region without needing any light from the object itself. The the bending of background light became a tool for mapping the unseen architecture of the cosmos. Weak gravitational lensing, a subtle form of this effect, became especially useful. It doesn't produce dramatic distortions but small, measurable changes in the shapes of distant galaxies. By analysing these slight shifts across many galaxies, astronomers could reconstruct the mass distribution in the foreground. This technique allowed the creation of large-scale maps covering significant portions of the sky. These maps didn't look like the familiar images of star fields or nebulae. They showed clumps, filaments, and broad regions of mass that did not correspond to visible structures. These were the shadows of dark matter, revealed through the way they bent light rather than through any light they produced. In cluster regions, strong gravitational lensing played an even more pronounced role. When mass concentrations were particularly high, they distorted background galaxies into arcs and stretched shapes. These distortions could be measured precisely, allowing astronomers to calculate the mass distribution with improved accuracy. Some clusters displayed striking differences between the distribution of visible matter and the mass indicated by lensing. In particular, certain clusters showed that the majority of the mass lay in regions almost empty of visible galaxies. The brightest parts of the cluster didn't necessarily align with the centre of gravity. This separation became one of the strongest indicators that the unseen component behaved differently from ordinary matter. One of the most well-known examples involved a pair of colliding galaxy clusters. When the clusters passed through each other, the visible gas collided and slowed down, creating a bright, hot region detectable through X-rays. However, the gravitational lensing map showed that most of the mass continued moving ahead of the gas, following the galaxies rather than the gas clouds. This separation between visible matter and gravitational mass provided compelling evidence that the unseen component did not interact with ordinary matter in the usual ways. The mass that kept moving didn't collide or heat up. It passed through with little resistance, showing that the unseen halos were not made of the same material as the gas or stars. These observations helped reinforce the idea that the hidden mass had properties fundamentally different from anything familiar. Mapping these shadows wasn't limited to clusters. Large-scale surveys aimed to trace the distribution of mass across the universe. These surveys combined gravitational lensing data with galaxy positions and cosmic microwave background measurements. The results revealed a web-like structure spanning enormous distances. Bright galaxies appeared along dense filaments, but the filaments themselves contained far more mass than the galaxies could account for. These structures connected clusters to one another, forming a network of mass that shaped the universe on scales beyond simple observation. These maps showed that the unseen component wasn't confined to the halos of individual galaxies. It filled the spaces between them, forming the backbone of the cosmic web. Even regions that appeared empty in optical images turned out to contain significant amounts of unseen mass when mapped through lensing. This changed the way astronomers understood the universe's large-scale structure. Instead of seeing isolated clusters floating in emptiness, the maps revealed interconnected pathways of mass, guiding the distribution of galaxies and influencing their motion. These pathways didn't align cleanly with visible structures. They extended into areas where no light-based observations showed anything of interest. Yet the gravitational influence showed that the region wasn't empty at all. These maps made it clear that the unseen mass contributed to the formation of structure across the entire universe. The maps also revealed variations in density, showing where the unseen component gathered more strongly and where it was more diffuse. This density variation shaped how galaxies formed, how clusters developed, and how matter moved over cosmic time. Regions with higher density attracted more visible matter, while regions with lower density became cosmic voids. The distribution of dark matter created the framework upon which the cosmic structure developed. It influenced everything from the spacing of galaxies to the shapes of clusters and the formation of filaments. These maps turned the concept of dark matter from an abstract idea into a measurable component of the universe's structure. Another method for mapping mass came from observing how galaxies cluster together at different distances. The pattern of clustering depends on how matter interacts gravitationally. If the universe contained only visible matter, the clustering patterns would differ significantly from what telescopes observe. By comparing these observations with simulations, astronomers inferred how much mass must be present in different regions. The results consistently showed more mass than visible matter provided. The clustering patterns matched models that included a dominant unseen component. This reinforced the idea that the unseen mass shaped the distribution of galaxies on large scales. Even within individual galaxies, more detailed mass maps became possible as measurements improved. Astronomers used stellar motions, gas dynamics, and sometimes lensing to reconstruct mass distributions. These maps revealed that dark matter halos typically extended much farther than the visible regions. In many cases, the halo stretched several times larger than the luminous disk. The stars appeared as a small central region embedded within an enormous mass reservoir. The details varied from galaxy to galaxy, but the overall pattern held. The visible matter wasn't the main contributor to the galaxy's gravitational field. It was only a small part of a larger structure defined by the unseen mass. Some galaxies provided exceptional opportunities for mapping. For example, certain galaxies appeared nearly edge-on from Earth's perspective, allowing better measurements of how stars moved along the vertical direction. This helped astronomers determine how mass was distributed, not only radially but vertically through the disk. These studies showed that visible matter couldn't account for the vertical motions of stars. Additional mass was required throughout the halo. These more detailed maps gave a clearer picture of how the unseen components surrounded the galaxy, influencing motion in ways that couldn't be explained by the luminous material alone. In other cases, dwarf galaxies offered compelling insights. These small galaxies often contained very little visible matter, yet their stars moved as though the galaxy held far more mass than observed. Because dwarf galaxies are simpler systems, with fewer interacting components, they provided clean environments for studying the unseen mass. The maps inferred from their stellar motions showed extreme ratios of unseen to visible matter. In some cases, the visible portion was barely detectable, yet the gravitational field remained strong. This showed that the unseen component wasn't simply proportional to visible material, it existed independently, dominating even in environments where visible matter was scarce. As these mapping methods evolved, astronomers developed more sophisticated simulations to compare with observations. These simulations incorporated both visible and unseen components, allowing researchers to test how different distributions affected the formation of galaxies and clusters. When simulations included the unseen mass, the resulting structures resembled the observed universe. When excluded, the structures differed significantly, failing to match many key features. The maps of the unseen mass therefore became essential for validating the models. They helped refine estimates of how much unseen material existed in different regions and how it influenced cosmic history. The mapping efforts also extended to the early universe. By studying the cosmic microwave background, astronomers could infer the distribution of matter shortly after the universe began. These early maps, though indirect, showed the seeds of future structure. The patterns in the background radiation revealed density fluctuations that later grew into galaxies and clusters. The amount of mass required to produce these fluctuations exceeded the visible matter by a large factor. This reinforced the conclusion that dark matter had shaped the universe from its earliest stages. The early maps matched the later maps, forming a coherent picture of unseen mass influencing structure across billions of years. Across all these approaches, the patterns were consistent. The unseen mass formed large halos around galaxies, filled clusters, extended through filaments, and shaped the cosmic web. The maps offered a way to visualize structures that light alone couldn't reveal. They didn't depend on the brightness of galaxies or the presence of stars. They reflected mass directly, through gravity's influence on motion and light. These maps changed the perception of space from a mostly empty backdrop to a dynamic landscape filled with unseen structures guiding the visible universe. When astronomers expanded their view beyond individual galaxies and clusters, they found that the universe wasn't arranged randomly. Instead, the distribution of matter followed patterns extending across enormous distances. These patterns weren't simple or uniform. They resembled a network of interconnected regions, with dense concentrations linked by elongated structures that stretched across space. These formations weren't obvious from looking at the light alone. They became noticeable only when large surveys were conducted, mapping the positions of countless galaxies across wide areas of the sky. As the data grew, the arrangement of galaxies began to reveal a structure that hinted at even larger underlying forces. The galaxies weren't drifting freely. They followed paths shaped by something that guided their distribution long before they became visible. The large surveys that attempted to measure galaxy positions didn't initially aim to uncover a web-like structure. They were designed to understand clustering, distances, and the expansion of the universe. As more observations accumulated, the emerging picture showed that galaxies tended to gather along elongated regions rather than spreading evenly. These formations connected clusters to one another, forming bridges of matter. Between these bridges were vast areas where few galaxies existed, creating large voids. This arrangement didn't resemble a random scattering of points. It indicated an underlying distribution of mass that shaped where galaxies could form and where they couldn't. The visible universe traced a kind of network, but the visible part represented only a fraction of the total mass shaping these structures. To understand why such a network formed, astronomers used computer simulations to model how matter moved under the influence of gravity over billions of years. When simulations included only visible matter, the resulting distribution looked too smooth and lacked the large structures seen in observations. But when the invisible component was included as the dominant form of mass, the simulated universe began forming a similar network to what the surveys revealed. The invisible mass shaped the gravitational potential across vast distances, creating regions where matter accumulated and regions where it didn't. The visible galaxies followed these patterns because they formed in the deeper gravitational wells created by the unseen material. These simulations showed that the universe's large-scale structure originated from small fluctuations in density, present shortly after the beginning. The fluctuations grew over time as gravity pulled material toward the slightly denser regions. The invisible component, unaffected by radiation, could begin collapsing earlier than visible matter. It created the groundwork upon which everything else would later build. As it clumped, it formed extended threads of mass connecting larger concentrations. These threads became the scaffolding of the cosmic web. Only after these structures formed did visible matter cool and settle into them, creating galaxies and clusters along the densest regions of the web. The term thread is not meant to imply something delicate or thin. The structures involved are enormous, stretching across tens or hundreds of millions of light years. They contain vast amounts of mass, most of which is invisible. Galaxies form along these threads like beads on a wire, gathering where the density is highest. The spaces between the threads are nearly empty, forming large voids where little mass accumulates. These voids aren't completely devoid of matter, but contain far less than the surrounding regions. Their existence reflects the distribution of the unseen component as it shapes where gravity creates the deepest wells. Mapping this web required combining multiple observational techniques. Surveys that charted the positions of galaxies provided the basic layout. Gravitational lensing filled in details about the underlying mass, showing where the unseen component was concentrated. Observations of the cosmic microwave background revealed the early seeds that eventually grew into the network. Together, these methods produced a coherent picture of a universe structured by invisible mass. Although galaxies illuminated the web itself was defined by the unseen component long before galaxies existed. The cosmic web isn't static. It changes over time as gravity continues to draw material inward. Clusters grow at the intersections of the web. Filaments stretch and evolve as matter flows along them. Galaxies move within these structures, guided by gravitational attraction. The unseen component shapes their movement, influencing how structures develop over billions of years. Simulations show that the flow of matter along filaments is a slow, steady process, driven by the gravitational pull of the densest regions. The unseen mass is the primary agent guiding this flow, with visible matter following suit. One of the most compelling aspects of the cosmic web is how well it matches predictions when the invisible component is included in models. This agreement wasn't guaranteed. The web-like structure could have been a coincidence or the result of some unknown mechanism, but the fact that simulations reproduce it only when the unseen mass is included provides strong support for the model. Without dark matter, the universe's structure would be dramatically different. Galaxies wouldn't cluster in the same way. Filaments wouldn't form. Voids wouldn't be as prominent. The entire cosmic landscape would lack the intricacy seen in observations. Astronomers also studied how galaxies within the web behave dynamically. Galaxies near filaments tend to move toward them, following the gravitational gradient created by the unseen mass. This motion, measured in large surveys, reveals the direction of mass flow across vast distances. The observations match the predictions of models that include dark matter. These flows help explain how clusters grow and why galaxies gather in specific regions. The visible universe moves along pathways defined by the invisible backbone of the cosmic web. Further insights came from observing how galaxies were distributed around filaments. They tended to align in particular ways, sometimes oriented along the direction of the filament. This alignment indicated that the gravitational forces shaping the galaxies didn't arise solely from visible matter, but from the larger structure of the web. The unseen mass created the environment that influenced how galaxies rotated, interacted, and evolved. Even subtle properties of galaxies, such as their orientation, carried information about the underlying dark matter distribution. The voids between filaments also provided valuable information. These large, nearly empty regions were sensitive to the distribution of the unseen mass. The size and shape of voids depended on how the invisible material gathered elsewhere. Observations show that voids had sizes consistent with models that included dark matter. They weren't random pockets of emptiness, but areas where the gravitational pull from surrounding structures dictated the flow of material. Understanding voids became just as important as studying dense regions, since both contributed to the full picture of how matter was arranged. The cosmic web revealed that dark matter didn't simply exist in isolated halos around galaxies. It extended across enormous distances, creating continuous structures that influenced the entire observable universe. The halos around galaxies connected to one another through filaments, forming an interconnected mass network. The visible matter existed within this network but didn't shape it. Instead, the web shaped the visible matter, determining where galaxies could form and how they would evolve. When astronomers looked at extremely distant galaxies, they saw early stages of web formation. These galaxies were forming in regions where the density of unseen mass was slightly higher. Even though the universe was younger and less developed, the early structures hinted at the same patterns seen today. The cosmic web didn't emerge suddenly. It grew gradually, shaped by the gravitational influence of the unseen component. The early universe showed small, faint structures that would eventually grow into the large filaments and clusters seen now. The connection between the cosmic web and the invisible mass also became evident when studying the temperature fluctuations in the cosmic microwave background. These faint variations reflected the density differences present shortly after the beginning of the universe. Over time, gravity amplified these differences, eventually producing the web-like structure. The amount of dark matter needed to match the observed fluctuations aligned with the amount needed to explain the distribution of galaxies and the large-scale network. This consistency across different epochs strengthened the case that dark matter shaped the universe from the earliest moments. While visible matter responded to the gravitational pull of the web, It also influenced the smaller scale details. Gas cooled and settled into the densest regions, forming stars and galaxies. These visible structures then interacted, merging and evolving. But the larger patterns guiding these events remained tied to the unseen mass. The visible matter could alter local regions, but couldn't change the overall shape of the web. The backbone remained defined by dark matter. As observational techniques improved, astronomers created more detailed reconstructions of the cosmic web. Large galaxy surveys provided enough data to map filaments in 3 dimensions. These maps showed the complex arrangement of clusters, voids, and connections stretching across space. The light from galaxies traced the web, but it was clear that most of the web's mass was hidden. The dark matter formed the structure, and the galaxies highlighted parts of it without revealing the full picture. Efforts to map dark matter directly continued through gravitational lensing studies. In some regions, the lensing data showed filaments that contained little visible matter, but large amounts of mass. These dark filaments were difficult to detect without lensing, yet they played an essential role in connecting clusters. Observations of these filaments provided further confirmation that the unseen mass was distributed across large-scale structures, not limited to halos around galaxies. These connecting regions were integral parts of the web, guiding matter flows across the universe. The cosmic web helped unify many aspects of cosmology. It connected the behavior of galaxies to the distribution of mass on the larger scales. It linked early universe fluctuations to present-day structures. It showed that the same unseen component responsible for galaxy rotation and cluster stability also shaped the universe's large-scale architecture. The dark matter wasn't acting in isolated pockets. It was influencing the cosmos as a whole. Understanding the web also provided insight into how galaxies gained their shapes and sizes. Galaxies forming at the intersections of filaments tended to grow larger due to the steady flow of matter from multiple directions. Smaller galaxies forming along filaments grew at slower rates. This variation depended on the mass distribution within the web. The unseen component determined the gravitational flow, and the visible components followed these paths. This relationship between the galaxies and the web explained many observed differences in galaxy types and sizes. As observations continued, the cosmic web became more detailed, showing smaller filaments branching from larger ones, connecting galaxies to clusters and clusters to superclusters. The complexity mirrored the simulations that included dark matter. Without dark matter, the patterns changed dramatically. The web either collapsed too quickly or didn't form strongly enough. The fact that observations matched simulations so closely when dark matter was included provided strong evidence for the invisible component's role in shaping the cosmos. The cosmic web remains one of the clearest demonstrations of how unseen mass directs the universe's evolution. It shows not only where matter accumulates, but how it moves and changes over time. The visible part paints only a partial picture. The underlying mass distribution, dominated by dark matter, creates the structure and guides the formation of everything that can be seen. As astronomers continued examining the universe through rotation curves, gravitational lensing and large-scale surveys, the patterns consistently pointed toward an unseen mass influencing everything. Accepting that something invisible existed was only the first step. Determining what it might be required understanding what it could not be. The process of elimination became as important as any direct measurement. Each possibility needed to be tested against the gravitational evidence, the distribution of galaxies, the behavior of clusters, the cosmic microwave background, and the way structures formed over billions of years. If a proposed explanation couldn't account for these observations, it had to be set aside. This slow narrowing of options helped shape our understanding of dark matter, not by revealing what it is directly, but by ruling out what it isn't. The first and most straightforward idea was that the missing mass might simply be ordinary matter that happened to be difficult to detect. Perhaps the universe contained countless dim stars too faint for telescopes to see. maybe large numbers of small cold objects such as brown dwarfs, rogue planets, or blackened stellar remnants drifted through space without producing light. These possibilities were practical and didn't require introducing anything unfamiliar. Many astronomers preferred these explanations initially because they fit comfortably within the known types of matter. If the missing mass could be accounted for by faint stars or cold objects, there would be no need for new physics. However, as observations expanded, this explanation began to fail. Surveys across a wide range of wavelengths attempted to detect faint stars and cold objects. Infrared surveys in particular were well suited for spotting dim, cool bodies. The results showed that while such objects certainly existed, they weren't abundant enough to account for the missing mass. The fraction of mass in faint stars and cold objects turned out to be far smaller than required. Even if every possible hidden object were counted, the total contribution remained a small part of what was needed to hold galaxies together. This ruled out the idea that the missing mass could be explained purely by faint stars or cold debris. Another idea was that dark clouds of gas might account for the missing mass. Gas can be challenging to detect if it's cold and doesn't emit much radiation, but gas interacts with light in other ways. It can absorb light from background sources or emit radiation from collisions between particles. Astronomers searched for signs of large quantities of cold gas using radio telescopes designed to detect specific emissions. The expected gas signatures did not appear in the necessary amounts. Furthermore, if the missing mass were mostly gas, the gas would influence the motion of stars and heat up through collisions. These effects weren't observed. Gas couldn't remain invisible in large quantities, so it couldn't account for most of the missing mass. Compact objects such as black holes were also considered. Small black holes, or large numbers of slightly larger ones, might provide mass without emitting light. But black holes interact gravitationally with their surroundings in ways that can be detected. If large numbers of them existed in galaxies, they would influence the distribution of stars more noticeably. Surveys also looked for microlensing events, brief changes in brightness caused when a compact object passes between Earth and a background star. These events can reveal the presence of compact objects even when they produce no light of their own. While microlensing studies did find some compact objects, they did not occur frequently enough to explain the missing mass. This ruled out the idea that galaxies were filled with large numbers of small black holes or similar compact remnants. Ordinary matter in any form interacts with radiation, either by absorbing, emitting, or scattering it. If the missing mass were ordinary matter, it would leave some trace in the electromagnetic spectrum. But observations across many wavelengths failed to reveal the necessary signal. This elimination process made it clear that dark matter could not be made of the same particles that form stars, planets, dust, or gas. The mass needed to stabilize galaxies and clusters had to be fundamentally different. It couldn't behave like ordinary matter or interact with light in the same way. This realization led researchers to consider new candidates beyond the familiar list of astronomical objects. Before exploring unknown types of particles, some scientists asked whether gravity itself might behave differently on large scales. If the law of gravity changed at great distances or under specific conditions, perhaps the missing mass wasn't missing at all. Instead, the equations used to estimate mass might need revision. This idea was appealing because it didn't require introducing new forms of matter. Instead, it adjusted the framework used to interpret observations. Modified gravity theories attempted to explain galaxy rotation curves without invoking unseen mass. Some models succeeded in matching certain observations, especially within individual galaxies. However, when these gravity modifications were tested against a wider range of data, problems emerged. The behavior of galaxy clusters couldn't be explained without additional mass. The lensing effects in systems where gas had separated from galaxies required a component that didn't interact with ordinary matter. The cosmic microwave background provided further constraints. The temperature fluctuations and their detailed patterns depended on the amount of mass present in the early universe. Modified gravity alone couldn't match these patterns. Simulations using only altered gravitational laws failed to reproduce the large-scale structure of the universe. They could explain specific observations, but not the full set. This ruled out the idea that gravity alone could solve the missing mass problem. The idea that neutrinos might account for the missing mass also surfaced. Neutrinos are abundant and have very low mass. They don't interact strongly with matter and pass through most objects without leaving any trace. In theory, if neutrinos had slightly more mass than expected, they might contribute significantly to the universe's mass budget. But neutrinos move at high speeds. This means they don't clump efficiently on small scales. Their rapid motion prevents them from forming dense regions early enough to seed galaxy formation in the way dark matter must. Studies of structure formation showed that neutrinos alone couldn't produce the observed cosmic web. They contributed a small amount of mass, but not nearly enough to account for the missing majority. Another possibility was that the missing mass was tied to errors in distance calculations or assumptions about how galaxies emitted light. Perhaps galaxies contained more stars than estimated, or perhaps dust obscured large regions of light. But improved measurements consistently reduced these uncertainties. Infrared and ultraviolet observations extended the range of detectable stars. Dust models were refined. Galaxy surveys increased in depth and coverage, yet the missing mass remained. The mismatch between visible matter and gravitational influence didn't shrink as data improved. It became clearer that the phenomenon was real, not the result of observational limitations. Some researchers considered whether exotic astrophysical objects could exist in vast numbers. These hypothetical objects might not behave like typical stars or planets. But theories predicting such objects required new physics without providing explanatory power beyond what dark matter models already offered. Without observational support, these ideas couldn't solve the missing mass problem and were gradually discarded. As more possibilities were eliminated, the focus narrowed to forms of matter that didn't interact with electromagnetic radiation at all. These forms of matter couldn't be hot gas, faint stars, dust, or compact objects. They couldn't behave like normal matter in the early universe. They had to avoid interacting with radiation while still contributing to gravity. This led to the conclusion that dark matter must be non-baryonic. In other words, it wasn't composed of the same type of particles that make up atoms. It didn't contain protons, neutrons, or electrons in the usual arrangement. It had to be composed of particles with mass, but without electromagnetic interactions. Ruling out normal matter helped shape this direction. The calculations from nucleosynthesis place strong limits on how much ordinary matter could exist in the universe. Observations of the cosmic microwave background reinforced these limits. If dark matter were made of ordinary matter, the early universe's temperature fluctuations and chemical abundances wouldn't match what was observed. These constraints were strong enough to eliminate the idea that dark matter could be a hidden form of familiar particles. As the elimination process continued, attention turned to unfamiliar particle types. These hypothetical particles would behave differently from anything already detected. They wouldn't absorb or emit light. They wouldn't form atoms or molecules. They wouldn't participate in chemical reactions. The only interaction needed was gravity. This meant they could be abundant without affecting radiation in measurable ways. Many particle candidates were proposed, but before exploring those possibilities, the process of elimination had to continue addressing other astrophysical explanations. One question remained whether dark matter could be explained by large-scale structures that hadn't been considered. Perhaps galaxies and clusters behave differently because of environmental effects or large-scale motions. But such explanations failed when tested against systems where dark matter clearly separated from visible matter. The behaviour of merging clusters, where the unseen mass stayed aligned with galaxies rather than gas, contradicted ideas of environmental misunderstanding. These observations required an additional component that didn't collide or slow down, unlike gas or stars. No alternative explanation could produce that result without invoking dark matter. Another idea considered whether black holes from the earliest moments of the universe, called primordial black holes, could be the missing mass. Unlike black holes formed from dying stars, primordial black holes could have formed shortly after the beginning, existing long before stars appeared. If they were present in vast numbers, they might supply the missing mass. This idea had theoretical appeal but required evidence. Surveys looking for microlensing events found some constraints. Studies of the cosmic microwave background placed limits on how many primordial black holes could exist without disrupting the observed radiation patterns. While some ranges of mass remained possible, primordial black holes couldn't account for all dark matter. They might exist in small numbers, but they couldn't explain the majority of the unseen mass. Through this gradual process of elimination, the range of viable explanations narrowed. Ordinary matter in all its known forms was excluded. Modified gravity couldn't explain all observations. Hot particles like neutrinos didn't fit the structure formation data. Large numbers of compact objects were ruled out by lensing surveys. Primordial black holes remained only a partial possibility. What remained was a type of matter that didn't behave like anything familiar. The invisible component had to be composed of particles that didn't interact with light, moved at speeds allowing them to clump early in cosmic history, and produced gravitational effects consistent with a wide range of observations. Eliminating the impossible didn't reveal what dark matter is, but it created a boundary around the problem. It made clear that the unseen mass had to satisfy a specific set of properties. It must be abundant, gravitationally influential, electrically neutral, and capable of forming the structures that shaped the universe. These constraints guided researchers toward examining new types of particles and models that might explain the missing mass. Once astronomers and physicists had ruled out every familiar form of matter, the search had to shift toward what could exist outside the boundaries of ordinary experience. The unseen mass-shaping galaxies, clusters, and the cosmic web had to be made of something capable of interacting through gravity while refusing to respond to light, heat, charge, or any of the conventional forces that let us detect matter directly. Since telescopes couldn't reveal it, the investigation turned to particle physics, where the idea emerged that the missing mass might come from a type of particle not yet discovered. These particles would have to satisfy the constraints established by decades of observations across astronomy and cosmology. They couldn't be fast-moving like neutrinos, they couldn't interact strongly with the electromagnetic radiation, and they had to gather into structures early in cosmic history. This shaped the search into one focused on particles that were massive enough to influence gravity, yet subtle enough to pass unnoticed through ordinary matter. When researchers first considered what particles might account for dark matter, they looked to existing theories in physics for guidance. Particles aren't invented out of convenience. They arise as possibilities within broader frameworks that aim to describe nature comprehensively. One of the earliest ideas was that dark matter might consist of weakly interacting massive particles, commonly called WIMPs. These hypothetical particles would interact only through gravity and the weak nuclear force. The weak nuclear force is responsible for certain types of particle decay, but doesn't influence everyday interactions, making it an appealing candidate for explaining matter that remains hidden. WIMPs would have masses much larger than neutrinos, allowing them to clump early in the universe without moving too quickly. They would be stable over cosmic timescales, resisting decay into lighter particles. This stability was essential because dark matter needed to persist throughout the history of the universe to continue shaping cosmic structures. The appeal of WIMPs came partly from a coincidence known as the WIMP miracle. According to early calculations, a particle with a mass and interaction strength similar to that expected for WIMPs would naturally produce the right amount of dark matter when the universe cooled after its hot beginning. As the universe expanded, particles formed, collided, and annihilated one another. If WIMPs existed, they would have been produced in abundance, and as the universe cooled, their annihilation rate would decrease until the remaining number stabilized. Remarkably, The predicted amount of leftover WIMPs aligned with the amount of dark matter inferred from astronomical observations. This coincidence made WIMPs an especially compelling possibility, tying together cosmology and particle physics in a way that seemed almost too convenient to ignore. Scientists began designing experiments to detect WIMPs directly. The idea was to observe occasional interactions between WIMPs and ordinary matter. Even though WIMPs would rarely interact, a large enough detector placed in a quiet environment might record one of these rare events. This led to the construction of underground facilities shielded from cosmic rays and other background signals. These detectors used techniques ranging from liquid xenon to cryogenic crystals to measure tiny amounts of energy released when a WIMP collided with an atomic nucleus. The hope was that a faint recoil would provide direct evidence of dark matter particles. As experiments improved, they became more sensitive, reaching levels where they should have detected WIMPs if the original predictions were correct. However, the expected signals didn't appear. Each new generation of detectors pushed the limits further, excluding wider ranges of possible WIMP masses and interaction strengths. The absence of detections began to raise questions. It didn't rule out WIMPs entirely since the range of possible properties was broad, but it made the simplest versions less likely. The fact that experiments became increasingly quiet suggested that if WIMPs existed, they might be far more elusive than originally thought, or interact even more weakly than predicted. While WIMPs received significant attention, they were not the only possibility. Another candidate emerged from efforts to solve a different problem in particle physics. This candidate was the Axion. The Axion was originally proposed to address a symmetry puzzle in the strong nuclear force, but physicists quickly realized that axions also had properties making them suitable dark matter candidates. Unlike WIMPs, axions were expected to be extremely light. They would interact so weakly with matter and radiation that they could pass through massive objects without leaving detectable traces. Despite their small mass, axions could exist in enormous numbers, collectively contributing significant mass on cosmic scales. Axions wouldn't behave like ordinary particles in the way they move or clump. They would form a kind of field permeating space, with slight variations in density providing the gravitational influence needed for dark matter. Detecting axions required different techniques from those used for WIMPs. One approach relied on the idea that axions could convert into photons under certain conditions. Experiments were designed using strong magnetic fields and sensitive detectors to look for faint signals that might be produced by axion photon conversion. These experiments needed to search through many possible frequencies because the mass of the axion was unknown. Progress was slow but steady, with experiments gradually expanding their search range. Like WIMPs, axions hadn't been detected yet, but they remained a strong possibility due to their ability to satisfy the physical requirements for dark matter. Beyond WIMPs and axions, there were other proposals involving particles predicted by theories attempting to unify known forces. Supersymmetry, a framework proposing that every known particle has a corresponding partner particle, offered several dark matter candidates. These partner particles would be heavier and more stable, making them good candidates for dark matter. Supersymmetry itself was developed to resolve theoretical issues in particle physics, not specifically to explain dark matter, but its predictions aligned conveniently with the need for new, stable particles. If supersymmetric particles existed, one of them might be stable enough to serve as dark matter. Particle accelerators, including those at large facilities, looked for signs of these particles by recreating high-energy collisions similar to those in the early universe. The hope was that such collisions would produce supersymmetric particles, revealing their presence through missing energy signatures. However, experimental runs didn't produce clear evidence for supersymmetry, leaving its dark matter candidates unconfirmed. Another set of ideas involved sterile neutrinos. Unlike regular neutrinos, which interact through the weak nuclear force, sterile neutrinos wouldn't interact through any force except gravity. They would be nearly impossible to detect directly, making them an appealing candidate for dark matter. Sterile neutrinos would also have masses different from those of ordinary neutrinos. If they were heavy enough, they might contribute significantly to the universe's overall mass. Their behaviour in the early universe would differ from that of traditional neutrinos, possibly allowing them to clump in ways consistent with dark matter. Searches for sterile neutrinos focused on indirect methods, such as looking for specific signatures in X-ray emissions that might indicate their decay. Some observations hinted at possible signals, but none were definitive. Physicists also considered even more unconventional possibilities. One idea was that dark matter might be composed of fuzzy particles, an extremely light type of particle whose wave-like nature could influence structure formation. These particles would be so light that their wavelength might stretch across entire galaxies. This would affect how matter clustered on small scales, potentially explaining some observed differences between simulations and real galaxies. If fuzzy particles existed, they could suppress the formation of very small structures while still allowing large ones to grow. This idea remained speculative but provided an intriguing avenue for matching detailed galactic properties. Other hypotheses included massive particles that interacted through their own force, separate from the ones already known. These particles could create self-interactions that might explain differences in density profiles within galaxies. Observations of galactic centers sometimes suggested a smoother distribution of dark matter than expected from simple models. Self-interacting dark matter could soften dense regions without affecting large-scale structure, providing one possible explanation. This idea was still developing, and researchers continued studying whether such interactions could match all observations. Some proposals stepped even farther from traditional physics. Concepts like hidden sectors suggested that dark matter might consist of entire families of particles interacting with one another through forces not connected to the ones familiar in the visible universe. These hidden sectors might have complex internal behaviour while remaining almost entirely separate from ordinary matter. Though speculative, these ideas illustrated how broad the range of possibilities had become. The more evidence excluded ordinary explanations, the more creativity researchers applied to particle models. Even with this wide variety of candidates, the search for dark matter remained grounded in the constraints established by cosmological observations. Any particle proposed as a candidate needed to satisfy several criteria. It had to account for the total amount of mass inferred from gravitational effects. It had to clump early in cosmic history, forming the seeds of galaxies. It had to interact weakly enough to avoid detection in past experiments, but strongly enough through gravity to influence structures. It had to remain stable over billions of years. It had to match the temperature fluctuations observed in the cosmic microwave background. And it had to be consistent with the distribution of matter in the cosmic web. These criteria helped rule out many possibilities while guiding ongoing research. Experiments continued refining their techniques. Some efforts focused on detecting faint signals produced when hypothetical particles interacted with magnetic fields. Others searched for signs of particle decay in space. Some experiments attempted to detect dark matter particles produced by cosmic rays interacting with the atmosphere or underground detectors. Each method targeted a different property of the potential particles. The absence of detection so far didn't imply that the particles didn't exist. It simply meant their properties might lie outside the current detection range. One challenge in the search was that dark matter might interact so weakly that detecting it directly could be extremely difficult. The detectors might need to become orders of magnitude more sensitive, or entirely new types of detectors might be necessary. Some researchers proposed building even larger underground facilities, or placing detectors in space where background noise would be lower. Others suggested developing new materials that might respond differently to hypothetical particles. These efforts illustrated the difficulty of the task. Detecting something that rarely interacts with ordinary matter required exceptional precision and patience. Despite the lack of direct detection, the theoretical work continued providing new ideas. Models exploring different masses, interactions, and behaviours created a broad landscape of possibilities. Some focused on particles too heavy to produce in current accelerators. Others examined extremely light particles requiring new detection methods. Each model attempted to match the constraints without introducing contradictions. The diversity of ideas reflected both the complexity of the problem and the determination to understand it. As the search expanded, researchers gained a deeper appreciation for the connection between dark matter and particle physics. The unseen mass wasn't just a curiosity in astronomy. It represented an opportunity to discover new physics beyond what was already known. The possibility of entirely new particles suggested that the universe contained layers of reality waiting to be uncovered. Even though dark matter remained hidden, the framework guiding its investigation grew stronger. The search for the unseen particles influencing the universe steadily led scientists toward a group of candidates that dominated discussions for many years. These candidates weren't chosen at random. They emerged from attempts to solve long-standing problems in particle physics while also fitting the requirements demanded by astronomical observations. The unseen mass needed to behave in a way that let it shape galaxies and clusters, form early structures, and remain stable over billions of years without interacting in noticeable ways with light or ordinary matter. Each particle candidate had to account for these features. Over time, a set of possibilities became central to the investigation, including weakly interacting massive particles, axions, and several other types of hypothetical particles that could slip through matter unnoticed. These ghostly candidates carried different properties, but all shared one essential characteristic. They could contribute mass without revealing themselves through electromagnetic interactions. Weakly interacting massive particles became a major focus because they arose naturally within several theoretical frameworks. If they existed, they would interact through gravity and the weak nuclear force, but not with light. This behaviour fit the need for dark matter to remain invisible while still influencing the motion of stars and galaxies. Early calculations showed that WIMPs could have been produced in large quantities during the early universe. As the universe cooled, they would have collided and annihilated at rates determined by their interaction strength. The predicted number left over would have aligned surprisingly well with the amount of unseen mass inferred from observations. This coincidence encouraged physicists to take WIMP seriously, since it offered a solution that connected particle physics and cosmology smoothly. Because WIMPs were expected to interact weakly with matter, researchers developed experiments designed to detect the tiny amounts of energy released when WIMPs bumped into atomic nuclei. These collisions would be rare, so detectors had to be built with extreme sensitivity. To reduce interference from cosmic rays and radiation, these detectors were placed deep underground in mines or specialized facilities carved into mountains. Some used large volumes of liquid xenon. Others used cryogenic crystals capable of measuring minuscule vibrations. The hope was that one of these detectors would eventually record a clear signal from a passing WIMP. Although early hints occasionally appeared, each one was eventually ruled out by further testing. This didn't end the search. Instead, it prompted researchers to build larger detectors, reduce background noise further, and refine the experimental methods. Despite these efforts, no confirmed WIMP signals have been observed. This absence of detection didn't eliminate the possibility entirely, since the properties of WIMPs were not precisely known. They could interact less frequently than expected or have different masses than originally predicted. Even so, the simplest versions of WIMP theories became less favoured as experiments excluded increasingly large regions of possible masses and interaction strengths. Physicists continued to test new models, but the optimism surrounding WIMPs gradually shifted to a more cautious outlook. The difficulty in detecting them suggested that if WIMPs existed, they might lie beyond the reach of current instruments. While WIMPs were receiving attention, another particle emerged from a different area of physics. Axions were proposed to resolve a symmetry issue in the strong nuclear force. Their introduction wasn't originally intended to solve the dark matter problem, but their properties aligned with what dark matter required. Axions would be extremely light, interacting so weakly with matter and radiation that they could pass through planets, stars and detectors without leaving clear signals. Yet their collective abundance could account for the unseen mass influencing the universe. Unlike WIMPs, axions wouldn't form in the same way during the early universe. Instead, they would behave more like a field that filled space. Their presence would be felt gravitationally without forming particles in the usual sense. Detecting axions required strategies very different from those used for WIMPs. One approach took advantage of the theoretical prediction that axions could convert into photons when passing through strong magnetic fields. Experiments were built to create controlled environments where this conversion might occur, using highly sensitive detectors to search for faint photons that shouldn't appear otherwise. These detectors swept through a range of frequencies because the mass of the axion, which determines the frequency of the converted photon, was unknown. The search moved slowly because each possible mass had to be tested individually. Although no confirmed axion detections had been made, the experiments continued expanding the range of frequencies examined. The results didn't rule out axions but narrowed the window where they might exist. Another reason axions remained appealing was that they didn't conflict with the structure formation of the universe. Their properties allowed them to contribute mass in a way that supported the formation of galaxies and clusters. They could clump on large scales while avoiding small-scale issues that arose in alternative models. Their weak interactions ensured they wouldn't disrupt the delicate balance of early universe conditions reflected in the cosmic microwave background. These features made axions viable candidates, even when WIMP searches produced null results. Other ghostly candidates emerged from theories attempting to extend the standard model of particle physics. Supersymmetry provided a rich collection of potential particles. This framework proposed that each known particle had a partner particle with different spin properties. Some of these partner particles could be stable, massive, and weakly interacting, making them plausible dark matter candidates. Supersymmetry offered an elegant solution to several theoretical issues, including how to stabilize particle masses and unify fundamental forces. If supersymmetric particles existed, one of them could account for dark matter. Particle accelerators attempted to create these particles by recreating high-energy conditions similar to those in the early universe. The strategy involved identifying events where energy vanished unexpectedly, suggesting the creation of particles that didn't interact with detectors. While accelerators observed many phenomena consistent with the standard model, clear signals of supersymmetric particles were absent. This didn't eliminate supersymmetry entirely, as the theory allowed partner particles to have a wide range of masses. They could lie beyond the reach of current accelerators, but the lack of evidence created uncertainty. Supersymmetry had been one of the most prominent theoretical frameworks, yet the missing signatures made it less convincing as a source of dark matter. Models were adjusted, but the absence of detection left researchers searching for alternatives. Another set of candidates included sterile neutrinos. Regular neutrinos interact through the weak nuclear force and gravity. They rarely interact with matter, which made them challenging to detect. Sterile neutrinos, however, wouldn't interact through the weak force at all. They would interact only through gravity, making them even harder to detect. Their existence was suggested to address certain anomalies in neutrino experiments. If sterile neutrinos existed with appropriate masses, they could serve as dark matter candidates. They would clump early enough in the universe to influence structure formation. Their decay might produce detectable X-ray signals. Some observations identified possible lines in X-ray spectra that might hint at sterile neutrino decay, but these signals remained unconfirmed. Physicists also explored models involving particles that were extraordinarily light. These included ideas where dark matter behaved as a wave rather than as individual particles. Such particles could have wavelengths spanning large regions of galaxies. Their wave-like behavior would smooth out small-scale structures and produce density profiles different from those predicted by WIMP models. These differences could potentially match certain observed galactic properties. Experiments to detect such particles required techniques sensitive to extremely low energy signals, pushing detection capabilities in new directions. Some theoretical models expanded the concept of dark matter to include hole-hidden sectors. These sectors could behave like a parallel version of particle physics, with their own internal interactions and structures. Particles in such sectors might interact among themselves through forces not connected to ordinary matter. These models could produce dark matter candidates with a range of behaviours, including self-interacting particles capable of explaining density differences within galaxies. Although speculative, these ideas reflected efforts to broaden the possibilities beyond traditional particles. The more researchers learned from observational constraints, the more they explored models that departed from conventional assumptions. Another idea involved massive composite particles formed from interactions not present in the visible universe. These particles could behave differently from elementary particles, remaining stable and abundant. Simulations examined whether such objects could form naturally and whether their presence would align with astrophysical observations. While these concepts remained mostly theoretical, they showed how wide-ranging the search had become. In all these cases, the hypothetical particles had to fit the detailed requirements established by the universe's behaviour. These requirements served as stringent tests. A candidate had to explain not only galaxy rotation curves but also the behaviour of clusters, the temperature fluctuations observed in the cosmic microwave background, the formation of the cosmic web, and the lack of electromagnetic interactions. It needed to remain stable across cosmic time and move at the right speeds to clump in the early universe. Many candidates failed some of these tests, allowing researchers to narrow their focus to the most promising possibilities. Experimental efforts continued in parallel with theoretical development. Some experiments focused on cryogenic detection methods, looking for tiny vibrations produced by particle collisions. Others measured photons produced in magnetic fields, hoping to see signs of Axion conversion. Large underground detectors monitored for rare events using liquids kept at precise temperatures. Particle accelerators sought missing energy signatures hinting at invisible particles. Observatories searched for X-ray or gamma-ray signals that might arise from particle decay. Each approach targeted a different aspect of these hypothetical particles, although none had provided definitive evidence yet. Each result refined the models, narrowing the parameter space where these particles might exist. The search for WIMPs continued through next-generation detectors, even as the simplest models became less favoured. The detectors grew larger and more sensitive, capable of probing weaker interaction strengths. New techniques were developed to distinguish potential signals from background noise. Some experiments used different target materials, hoping that varying the atomic properties might reveal patterns indicating WIMP interactions. Theoretical models expanded to include broader ranges of masses and interaction types, keeping the possibility alive. Axion experiments also advanced. Improvements in magnet design, detector sensitivity, and scanning speeds allowed researchers to explore wider frequency ranges. New proposals suggested searching for Axion-like particles in entirely different ways, such as through astrophysical signals or effects on electromagnetic fields. Axions remained viable because they could account for dark matter without conflicting with known observations, even though they demanded a challenging form of detection. Sterile neutrinos continued to be investigated indirectly. Astronomers examined X-ray emissions from galaxies and clusters, looking for unusual spectral lines that might imply decay. Although occasional hints emerged, none were confirmed. More sensitive telescopes and improved analysis techniques were expected to provide clearer answers in the future. The breadth of these ghostly candidates reflected the difficulty of the problem. Dark matter had to be something subtle enough to avoid detection for decades, while influencing the universe on the largest scales. It needed to be stable, abundant, and gravitationally effective. Each candidate particle attempted to satisfy these conditions in different ways, and each required a combination of theoretical reasoning and experimental testing to evaluate. As the list of possible dark matter particles grew, the challenge of detecting them remained a central concern. If these particles interacted so weakly with ordinary matter that they passed through planets, stars, and detectors without leaving measurable traces, finding evidence of them required extraordinary care. Researchers began building experiments designed not to catch loud or obvious signals, but to detect incredibly faint disturbances. These disturbances would be so subtle that they resembled footsteps too light to press into dust, yet still meaningful if measured with enough precision. The experiments needed to listen to the universe with an attention that pushed the limits of technology, reducing noise from every possible source until only the quietest hints remained. The task wasn't simply one of building big machines. It was one of isolation, patience, and an understanding of how easily a single unrelated signal could mimic what the researchers were searching for. Deep underground laboratories became central to this effort. To detect signals from particles that rarely interacted with matter, the detectors had to be shielded from other particles that interacted frequently. Cosmic rays, which constantly bombard Earth's surface, would overwhelm the sensitive equipment if allowed to reach the detectors. By placing experiments beneath mountains or inside mine shafts, researchers used the Earth itself as a shield. The layers of rock absorbed most of the incoming cosmic rays, reducing background noise to levels that allowed the detectors to search for weak interactions. Entering these facilities often required passing through long tunnels and controlled chambers where every variable was monitored. Even small changes in temperature or humidity could influence the way detectors behaved, so the environment had to remain stable. Once inside, many of these detectors used large volumes of materials chosen for their sensitivity to tiny energy deposits. Liquid xenon became one of the most widely used materials because it produced light and electrons when struck by particles. When a particle collided with a xenon atom, the detector could measure a faint flash of light and a tiny electrical signal. By analysing the timing and position of these signals within the detector, researchers could determine whether they resembled what would be expected from dark matter interactions rather than background radiation. The experiments had to distinguish between ordinary noise, subtle chemical processes, radioactive impurities, and the rare collisions sought. Even slight contamination in the xenon could mimic a signal, so the purification process had to be extremely thorough. Other experiments relied on cryogenic crystals cooled to temperatures near absolute zero. At such low temperatures, the crystals became incredibly sensitive to small vibrations. If a dark matter particle deposited a tiny amount of energy into the crystal, that energy could produce measurable effects. The detectors could distinguish between different types of interactions by analysing how the energy spread through the material. Vibrational signals from ordinary particles tended to have specific patterns, while hypothetical dark matter particles were expected to create different patterns. Maintaining temperatures so low required complex refrigeration systems that had to run continuously without interruption. In all these experiments, controlling noise was as important as detecting the signal itself. Researchers had to understand every source of background radiation present in the detector. This meant identifying radioactive isotopes in the materials used to build the detectors, measuring the activity levels of the components, and ensuring that the surrounding rock didn't emit stray signals. Even the air inside the chambers had to be monitored, since radon gas could introduce unwanted particles into the detector. Reducing these sources of noise required meticulous design choices and careful selection of construction materials. Despite the complexity, several experiments operated continuously for months or even years, gradually collecting data. Each recorded event had to be analysed to determine whether it matched the expected signature of dark matter. Most events could be attributed to known sources. A small number remained ambiguous, prompting researchers to refine their analysis techniques. Occasionally, hints emerged that sparked interest. These hints required verification from multiple detectors to avoid premature conclusions. When signals appeared in only a single detector and wasn't observed elsewhere, the scientific community approached them cautiously. Sometimes these hints eventually disappeared as new data came in, or as additional sources of noise were identified. While underground detectors listened for collisions, other experiments searched for particle interactions in different ways. Some looked for dark matter particles produced naturally in cosmic environments. If certain particles could decay into photons or other detectable particles, telescopes on Earth and in orbit might observe these decay signals. Observations of galaxies and clusters provided opportunities to measure X-rays or gamma rays that might come from dark matter decay. If a specific energy line appeared consistently in multiple observations, it could indicate a particular particle mass. Several studies produced potential signals, but none were confirmed as dark matter. Each time a candidate line appeared, further observations were needed to determine whether it originated from dark matter or from a more ordinary process such as interactions within hot gases. A different strategy involved searching for signs of dark matter in particle accelerators. By colliding particles at high energies, accelerators could produce new particles that didn't appear in everyday environments. If dark matter particles could be created in these collisions, they wouldn't interact with the detectors directly. Instead, they would escape without leaving tracks. The detectors would observe missing energy and momentum. Physicists used this missing information to infer the presence of potentially invisible particles. These experiments required precise control of the collision environment, sophisticated detectors to measure the outgoing particles, and theoretical models to interpret the missing energy. Although accelerators produced many unusual events, no clear signal of dark matter particles appeared. Some experiments turned to astroparticle methods, looking for the products of interactions between dark matter particles and cosmic rays. If dark matter particles occasionally annihilated or decayed, the process might produce ordinary particles that could be detected. Space-based detectors measured the flux of electrons, positrons and gamma rays. Any excess beyond expected background levels could hint at dark matter interactions. These observations were challenging to interpret because many astrophysical processes could generate similar signals. Pulsars, supernova remnants, and other energetic objects created emissions that complicated the analysis. Even so, researchers used these data to test various dark matter models and explore whether certain interaction types were plausible. As the effort expanded, some experiments used approaches that were more imaginative and less conventional. Certain theoretical models suggested that dark matter particles might interact with electromagnetic fields in extremely subtle ways. Experiments built to test these ideas looked for small changes in field behavior under controlled conditions. Other proposals suggested detecting the gravitational influence of individual particles, although this remained far beyond current technological capabilities. These theoretical explorations encouraged the development of new detection techniques, even if some remained speculative. One of the quiet challenges in searching for dark matter was knowing where to look. If dark matter was distributed throughout the universe, it would also pass through Earth in large numbers. But without knowing how frequently it interacted with matter, experiments had to be built assuming a broad range of possible interaction strengths. The rate of interaction could be so low that decades of data collection might be required. This meant that even when experiments didn't detect anything, they still contributed valuable information. Each null result helped exclude certain models, narrowing the possibilities and guiding future searches. The search for dark matter wasn't limited to individual detectors or isolated experiments. Collaborations across countries and institutions shared data, coordinated strategies, and compared results. Experiments in different parts of the world used different materials, environments, and detection methods. This diversity ensured that no single source of noise or environmental factor could mislead the entire field. If a signal appeared in multiple independent experiments, it would carry more weight. If it appeared only in one, researchers would examine whether the environment or equipment might have caused it. The importance of redundancy extended to theoretical models as well. Physicists used the results from different experiments to evaluate how likely each candidate particle was. If underground detectors excluded certain interaction strengths and accelerators excluded specific mass ranges, those excluded regions guided theorists toward alternatives. Simulations that included dark matter interactions helped refine what properties the particles needed to have in order to match observations. The interplay between theory and experiment created a continuous feedback loop that improved both approaches. Some experiments aimed at detecting axions used resonant cavities combined with strong magnetic fields. The idea was that if axions passed through the cavity, they might convert into photons at specific frequencies depending on their mass. This required tuning the cavity to different frequencies and monitoring for faint signals. The challenge lay in scanning a vast frequency range since the mass of the axion was unknown. Researchers had to adjust the apparatus gradually, scanning one narrow interval at a time. As the searches continued, improvements in detector sensitivity and cavity design accelerated the pace. Newer concepts explored techniques that didn't rely on traditional cavity designs. Some used plasma effects, while others employed specialized materials that might respond differently to axion-like particles. These alternative methods broadened the search, providing opportunities to test additional mass ranges. The difficulty remained the same, detecting a particle that interacted so weakly that it might pass through the entire Earth without leaving a mark. Yet each improvement brought researchers closer to probing a greater portion of the possible parameter space. The ongoing effort to detect dark matter also inspired experiments aimed at observing dark matter interactions with astrophysical bodies. Some models predicted that dark matter could accumulate inside stars or planets over time, potentially influencing their behavior. Exotic interactions might affect energy transport within stars or change their cooling rates. Researchers examined white dwarfs, neutron stars, and even Earth for signatures that might reveal indirect evidence of dark matter. Although these studies hadn't produced definitive results, they provided new avenues for exploring the unseen particles. Regardless of which method researchers used, the overarching challenge remained capturing a signal faint enough that it blended almost entirely into the background. The technological requirements pushed engineering and material science to new limits. Detectors needed to be built from materials with extremely low levels of radioactivity. Sensors needed to measure energy deposits so small that they would have been dismissed as noise in any other field. Environmental monitoring systems had to maintain stable conditions for months or years. Each detail had to be considered, because the slightest flaw could produce a misleading signal. The willingness to build such sensitive instruments reflected an understanding that dark matter wouldn't be revealed through ordinary means. It wasn't something that could be photographed, captured, or held. Detecting it required patience and attention to the smallest disturbances in systems designed to be as quiet as possible. These experiments didn't wait for dramatic events. They waited for rare, tiny interactions that occurred with almost unimaginable infrequency. As experiments continued listening for faint interactions, researchers also explored the possibility that the unseen particles influencing cosmic structure might occasionally collide with one another or produce signals too subtle to appear in ordinary environments. If dark matter particles interacted even slightly, those interactions could leave measurable effects under the right circumstances. Astronomers studied distant galaxies, clusters, and the patterns in cosmic radiation for any sign that these particles produced energy, radiation, or unusual features that couldn't be explained by visible matter alone. The hope was that somewhere in those distant environments, dark matter would reveal something about itself through a rare interaction or a collision that generated detectable byproducts. Each new observation method provided a way to test whether the unseen mass could be more than just gravitationally influential. But the search brought challenges because the signals expected were faint, and the environments being observed contained many processes capable of producing similar effects. Disentangling one from another became a patient exercise in comparing theory, observation, and simulation. One place where researchers looked for signs of dark matter interactions was in the centres of galaxies, where densities tended to be highest. If dark matter particles occasionally collided and annihilated, the process could release energy in the form of photons or other particles. These emissions might appear as excess radiation at specific wavelengths, standing out from the usual astrophysical processes that occur near stars, gas clouds, and black holes. Some telescopes scanned the central region of the Milky Way, searching for gamma rays that might indicate dark matter annihilation. This region was a natural target because it contained enough matter to potentially increase the chances of dark matter interactions, while still being close enough to observe in detail. Early studies reported a possible gamma ray excess that didn't match ordinary sources. This sparked interest, since the signal resembled predictions for certain dark matter models. But as researchers studied the region more closely, they found that pulsars and other astrophysical objects could produce similar excesses. The data had to be scrutinized carefully to determine whether the excess truly reflected dark matter collisions, or whether it arose from populations of faint objects that hadn't been catalogued. The complexity of the galactic centre made it difficult to isolate any one process. Every time a possible signal appeared, additional data and analysis were needed to rule out alternative explanations. As the observations improved, many of the early hints became less convincing. Some disappeared entirely once updated models accounted for previously unknown sources of radiation. Others persisted but became more ambiguous, leaving open the possibility but offering no confirmation. Researchers also examined dwarf galaxies orbiting the Milky Way. These galaxies were ideal targets because they contained very little gas and few stars, reducing the number of astrophysical processes that could mimic signals. If dark matter collisions produced gamma rays or X-rays, they might appear more clearly in these quiet environments. Several studies searched for signals in these galaxies, but the results didn't show any consistent emissions above background noise. This absence didn't rule out dark matter interactions, but did constrain how strong those interactions could be. If collisions occurred, they had to be rare or weak enough that their signatures didn't appear even in the cleanest environments. Beyond gamma rays, scientists looked for other possible signals from dark matter interactions. Some models suggested that dark matter particles might decay over billions of years, producing narrow spectral lines in X-ray observations. Telescopes capable of detecting faint X-ray lines began scanning clusters and galaxies for unexpected features. A few studies reported lines that didn't match known atomic transitions, prompting speculation about possible dark matter decay. But follow-up observations often fail to reproduce the same results. In other cases, the lines seem to vary with instrumental sensitivities or calibration issues, raising doubts about whether they reflected real astrophysical phenomena or artifacts of the measurement process. This pattern repeated across different searches. Signals emerged, drew interest, and ultimately faded as more data accumulated. Another area of investigation analysed high-energy particles detected by space-based instruments. If dark matter particles annihilated or collided in certain environments, they could produce electrons, positrons, or other energetic particles. Instruments studying cosmic rays measured the abundance of these particles across various energy ranges. At times, the results suggested slight excesses that didn't align perfectly with known astrophysical processes. These excesses prompted speculation about dark matter contributions, but the interpretation was complicated because pulsars and other energetic objects could create similar patterns. Distinguishing between the contributions of dark matter and conventional sources required detailed modelling. As models improved, many of the excesses became explainable without invoking dark matter. They remained interesting but inconclusive. The search for dark matter collisions extended to galaxy clusters as well. These enormous structures contained large amounts of dark matter and provided an environment where interactions might be more likely detectable. Telescopes scanned clusters for unusual radiation or signals that could originate from dark matter interactions. Some studies examined how dark matter behaved during collisions between two clusters. If dark matter particles interacted with one another, they might slow down or scatter during large-scale collisions. Observations of cluster mergers provided opportunities to compare how dark matter and visible matter behaved. Most studies showed that dark matter passed through these interactions without noticeable resistance, reinforcing the idea that dark matter interacted extremely weakly, not only with ordinary matter but also with itself. This behavior limited the range of possible self-interactions, ruling out models where dark matter particles collided frequently. Despite these constraints, some models allowing mild self-interactions remained possible. These models suggested that dark matter might scatter, rarely but measurably, in environments with high density. Observations continued to test these possibilities, comparing the distribution of dark matter inferred through gravitational lensing with the distribution of visible matter. While some simulations showed that slight interactions could produce small changes in density profiles, the observational evidence remained difficult to interpret. The differences between simulated and observed galaxies could often be attributed to other factors, such as the influence of gas physics or star formation. As a result, attempts to use galactic structures to test for dark matter self-interactions produced mixed results, offering no clear confirmation. One of the persistent themes in these searches was the presence of signals that initially appeared promising, but grew weaker under scrutiny. This pattern became familiar across many studies. A potential gamma-ray excess might follow a predicted shape, only to be explained later by faint astrophysical sources. A narrow X-ray line might appear in one instrument but not another. A cosmic ray anomaly might persist until additional data revealed a conventional explanation. These quiet disappointments didn't discourage the field but highlighted the difficulty of detecting something that interacted so rarely. They reinforced the need for caution in interpreting results and the importance of multiple, independent measurements. Another challenge came from the limitations of the instruments themselves. Telescopes had sensitivities that varied across energy ranges. Calibration had to be precise to avoid misinterpreting instrumental noise as a real signal. Data analysis techniques evolved as researchers learned more about the instruments, reinterpreting earlier results with greater sophistication. Sometimes an apparent signal disappeared entirely when reanalyzed with improved calibration. Other times, the signal remained ambiguous because the noise levels were too high to draw firm conclusions. In each case, the challenge of distinguishing faint signals from background fluctuations became more apparent. Even the environments targeted for observation posed difficulties. Regions with high dark matter density also tended to contain numerous astrophysical processes, complicating interpretation. Regions with low astrophysical activity often had lower dark matter density, reducing the expected signal strength. Finding the right balance between these extremes required carefully selecting targets and adjusting observational strategies. Some studies focused on specific clusters known to have well-characterized mass distributions. Others examined multiple dwarf galaxies simultaneously to improve the statistical significance of potential signals. Despite these strategies, the results remained inconclusive. Simulations continued to play a crucial role in interpreting observational results. They provided insight into how dark matter might behave under various conditions, helping researchers understand what signals to expect. These simulations incorporated gravitational effects, particle interactions, and astrophysical processes. By comparing simulated signals with observational data, researchers could determine whether a particular model matched reality. In many cases, the simulation showed that dark matter self-interactions needed to be extremely weak to avoid contradicting observations of cluster mergers or galactic dynamics. This eliminated models that predicted strong interactions, but still left a broad range of possibilities open. The gradual accumulation of null results didn't diminish the importance of the search. Each study refined the understanding of what dark matter could be. Each quiet disappointment narrowed the field of possibilities, guiding researchers toward models that better match the universe's behavior. The absence of strong signals didn't rule out dark matter interactions entirely. It simply indicated that they were likely faint, rare, or confined to conditions not yet accessible to observation. The continuing effort focused on improving instrument sensitivity, expanding observational coverage, and exploring new detection methods. In addition to scanning cosmic environments, researchers considered whether dark matter interactions might appear in time-varying signals. Some models suggested that dark matter density near Earth might fluctuate, producing periodic changes in detector signals. Experiments began looking for annual modulation, a slight variation in detection rates due to Earth's movement through the galaxy. One experiment reported a modulation that persisted over many years, generating significant interest. However, other detectors using similar methods failed to observe the same pattern. This discrepancy led to debates about whether the modulation reflected real dark matter interactions or arose from environmental or instrumental effects. The possibility remained open, but the lack of independent confirmation made it uncertain. Newer instruments aim to detect even more subtle signals, pushing the sensitivity limits further. Some detectors attempted to measure phonons, tiny vibrations in materials caused by extremely faint energy deposits. Others focused on detecting low-mass particles that might have eluded earlier searches. These efforts broadened the range of signals that could be tested, but they also highlighted the challenges of distinguishing genuine events from background activity. Each new method brought the promise of discovery, balanced by the likelihood of additional quiet disappointments. Despite the difficulties, the search served a crucial role in shaping theoretical work. As observational limits tightened, theorists adjusted their models. Possibilities that once seemed promising became less viable as data excluded their predictions. New models emerged that matched the refined constraints. This interplay ensured that research progressed even without direct detections. Dark matter remained an unknown, but its behavioral boundaries became better defined. The unseen mass needed to satisfy increasingly specific conditions, shaping how future experiments targeted their searches. As the years passed and experiments continued returning results that narrowed the range of dark matter candidates without confirming any of them, scientists considered whether the invisible mass inferred throughout the universe might not be a new type of particle at all. Instead, perhaps the underlying rules governing gravity behaved differently in certain conditions. This idea didn't arise from a lack of interest in particle explanations, but from the recognition that gravity itself was notoriously difficult to test at the extremes of cosmic scales. Much of physics involved forces understood through direct experimentation, but gravity, being the weakest of the four known forces, resisted careful scrutiny in many situations. If gravity changed its behavior at large distances or low accelerations, it might produce effects resembling those attributed to unseen matter. This possibility encouraged researchers to explore alternatives that adjusted gravitational laws rather than adding new forms of material. The motivation for these attempts often came directly from galactic rotation curves. Stars in the outer regions of galaxies were moving too quickly to remain bound by visible matter alone. One interpretation was that an unseen halo of mass provided the necessary gravitational pull. Another interpretation was that gravity itself became stronger, or behaved differently at low accelerations. If gravity didn't follow the traditional inverse square law in such conditions, the star's speeds might not require extra mass. One of the earliest and most discussed alternatives proposed that gravitational acceleration underwent a subtle shift at low levels. This framework didn't discard gravity entirely, but suggested that the familiar laws needed slight adjustments under specific circumstances. The idea was attractive because it attempted to explain galactic behaviour without invoking large quantities of unseen matter. This approach succeeded in describing some galactic rotation curves remarkably well. With a modified version of gravitational acceleration, the motion of stars in many galaxies followed predictable patterns without adding dark matter. This early success encouraged further exploration. Researchers examined how the modified laws behaved in different galaxies, and the results often matched observed rotation curves. But while this method seemed promising on smaller scales, it encountered problems when applied to larger systems. Galaxy clusters presented a major challenge. The difference between visible mass and gravitational influence in clusters was much larger than in individual galaxies. Even with modified gravity, additional mass still seemed necessary. The adjustments that worked for galaxies didn't explain the cluster scale discrepancies. Gravitational lensing provided another test. If gravity behaved differently in certain ways, the bending of light around galaxies and clusters should reflect those new rules. But lensing measurements often aligned closely with predictions that included dark matter, halos rather than modified gravity alone. Particularly in merging clusters where visible matter separated from gravitational mass, modified gravity frameworks struggled. The gravitational signal followed galaxies, not gas, suggesting a form of mass that didn't interact like ordinary matter. Modified gravity couldn't easily separate gravitational influence from visible material unless additional hypotheses were added, making the models more complex than originally intended. Researchers continued refining these alternative frameworks to better match observations. Some proposed more detailed mathematical adjustments to how gravity operated at various scales. These adjustments allowed for certain successes, especially with individual galaxies, but often required fine-tuning that reduced their overall simplicity. A theory that explained one class of objects well sometimes failed when tested against another. The variety of cosmic structures meant that any alternative to dark matter had to match observations across a wide range of scales, from dwarf galaxies to massive clusters, and from early universe fluctuations to present-day structures. Another observational challenge came from the cosmic microwave background. The temperature fluctuations across this faint radiation formed shortly after the universe began. Their properties depended on the amount of mass present at that early time. Models attempting to remove dark matter and modify gravity struggled to reproduce these fluctuations accurately. They required significant adjustments to match the observed patterns, including the relative heights of peaks in the fluctuation spectrum. Dark matter models reproduced these patterns naturally with few additional assumptions. Modified gravity models needed additional parameters, making them less appealing from a simplicity standpoint. The cosmic web added further difficulty. Large-scale simulations showed that without dark matter, or without a mechanism producing similar gravitational effects early in the universe, the filaments connecting galaxies and clusters would not form as observed. Modified gravity theories attempted to produce these structures by adjusting gravitational behavior, but the process became increasingly complex. Simulations had to incorporate layers of gravitational rules depending on environment, scale, and acceleration. Even then, some versions failed to match the density contrast present in real observations. Others created structures too diffuse or arranged differently from surveys. Despite these issues, the exploration continued because understanding gravity remained fundamental to cosmology. Researchers revisited the equations governing gravitational force and considered whether extensions of general relativity might produce effects resembling dark matter. Some proposed that gravity might include an additional component at large scales, similar to how earlier discoveries revealed hidden elements in other forces. These ideas didn't eliminate dark matter entirely, but attempted to share the explanatory load between modified gravity and unseen mass. In some versions, gravity contained extra fields or terms that altered its behavior depending on distance or matter density. This allowed gravity to behave differently in galaxies than in clusters, addressing one of the common problems of simpler modifications. These extended theories produced a diverse range of predictions. Some matched galactic rotation curves while retaining consistency with gravitational lensing data. Others attempted to reproduce the cosmic microwave background patterns more accurately. But achieving success across all these observations remained difficult. The complexity of the universe's structure demanded a theory capable of addressing multiple phenomena without conflicting results. While the alternative gravity models became more sophisticated, dark matter remained a simpler explanation for many observations. The unseen mass could be incorporated consistently across scales, while modified gravity often had to adapt in different ways depending on context. Another reason modified gravity faced challenges was the behavior of merging clusters. Observations of clusters passing through one another revealed a separation between visible gas and gravitational mass. The gravitational influence followed galaxies, not gas. In a modified gravity scenario, gravitational influence should follow visible matter, unless special conditions applied. Some theories attempted to account for this by adding additional fields that tracked galaxy positions differently from gas, but these additions made the models increasingly complex. Each new layer made the theory harder to justify, compared to the simpler idea that clusters contained large amounts of unseen mass. As alternative gravity theories grew more complicated, researchers compared how many assumptions were required for each approach. The dark matter hypothesis introduced a new form of matter but didn't require changes to gravitational laws. Modified gravity theories kept the laws of matter unchanged but introduced new gravitational behaviors or fields. Both approaches introduced something new. The question became one of explanatory power. Which approach required fewer assumptions while matching more observations? For many, dark matter provided the more efficient solution, but the exploration of modified gravity still contributed valuable insights. It improved understanding of how gravity behaved in various contexts and pushed researchers to examine assumptions that might otherwise go unquestioned. It also encouraged the development of tests capable of distinguishing between modified gravity and dark matter scenarios. These tests often involved precise measurements of gravitational lensing, galaxy motion, or the behavior of systems with little visible material. Some galaxies with extremely low star counts provided natural laboratories. If gravity behaved differently at low accelerations, these systems should reflect that behavior clearly. Observations of such galaxies helped test whether modified gravity models could reproduce the data. Some models performed reasonably well, but many struggled when confronted with the full variety of galactic environments. There were also tests involving the internal motions of stars within galaxies. Modified gravity theories predicted specific relationships between mass distribution and stellar velocities. While these predictions matched some galaxies, others deviated from the expected patterns. Dark matter, with its flexibility and distribution, explained these deviations without difficulty. The more galaxies observed, the more variation appeared in their structures. Modified gravity needed to account for all of them consistently, which remained difficult. Despite these challenges, the exploration of modified gravity inspired broader thinking about the universe. It encouraged researchers to consider whether cosmic behavior might reveal unknown aspects of gravity. Even if these theories didn't ultimately replace dark matter, the process strengthened the understanding of how gravitational forces might be extended or refined. Some hybrid models emerged, combining elements of dark matter with modified gravity. These models attempted to capture the strengths of each approach while avoiding their weaknesses. They were speculative, but reflected an effort to produce unified explanations. As modified gravity theories evolved, they also drew from advances in understanding dark energy, the phenomenon driving the accelerated expansion of the universe. Some frameworks attempted to connect dark matter and dark energy in a single model, altering gravitational behavior to explain both. These attempts remained preliminary, but they illustrated how intertwined cosmic mysteries could become. While dark matter and dark energy were distinct phenomena observationally, they both suggested limits in current understanding of gravity and cosmic structure. The development of alternative gravity ideas reinforced the importance of testing every assumption. It wasn't sufficient to accept dark matter without considering whether gravity behaved differently at scales far beyond daily experience. This scrutiny ensured that the dark matter hypothesis remained robust rather than unquestioned. Each new test of gravity provided opportunities to refine understanding, eliminate weaker ideas, and strengthen the foundations of cosmology. At the same time, the growing list of successful predictions made by dark matter models, especially when combined with simulations, made them challenging to replace. Modified gravity could mimic certain features but struggled with the wide range of observations accumulated over decades. The separation between visible and gravitational mass in clusters, the patterns in the cosmic microwave background, the structure of the cosmic web, and the behavior of galaxies all aligned more naturally with the presence of unseen mass. The simplicity of adding a new form of matter outweighed the complexity of rewriting gravitational laws in many cases. Still, modified gravity remained valuable as a point of comparison. Any new theory of the universe needed to match or exceed the explanatory power of dark matter. By exploring alternatives, researchers could test the limits of what gravity alone might accomplish. This comparative approach strengthened confidence in dark matter, while revealing areas where gravitational understanding might require refinement. From the earliest hints in galaxy rotation curves to the wide lattice of the cosmic web stretching across billions of light-years, the influence of dark matter has appeared again and again in ways that define the universe far more thoroughly than the material we can see. And yet, this component that governs motion on the grandest scales never touches us in any familiar sense. It surrounds Earth, moves through it, fills the spaces between stars, and guides the formation of every structure that has ever emerged. But it does so silently and without leaving marks that our senses or everyday tools can detect. The paradox rests in this contrast between its enormous importance and its refusal to interact directly with anything around us. Even so, its presence can be traced through consequences so consistent and widespread that its influence becomes unavoidable in nearly every astronomical measurement. The familiar matter we know, atoms, molecules, dust, gas, planets, stars, form structures because of gravity drawing material together. That process depends heavily on how mass is distributed. In regions where mass is abundant, gravitational pull becomes stronger, making it easier for gas to collapse and form stars or galaxies. In areas with little mass, the process stalls, leaving expanses of nearly empty space. Dark matter dictates where these zones appear. Even before the first stars formed, dark matter had already collected into clumps that created gravitational wells, deep enough to pull in ordinary matter once the universe cooled. These early structures weren't visible, but they shaped everything that followed. When gas began falling into these wells, galaxies eventually formed at their centres. Without these wells, the observable universe would look nothing like it does today. This pattern continues across every scale. On the smallest galactic levels, the distribution of dark matter determines how fast stars move, how stable their orbits remain, and how a galaxy expands or contracts over time. A galaxy with a dense central region of dark matter will hold its stars more tightly, producing rotation curves that maintain speed far beyond the visible edge. A galaxy with a less concentrated region of dark matter will show a different rotation pattern. Even the shapes of galaxies reflect this invisible framework. Spiral galaxies with long, extended arms rely on the support of a dark matter halo to maintain their structure. Without it, the arms would unwind over time, losing their familiar appearance. When astronomers model the internal structure of galaxies, they find that visible matter alone cannot reproduce the observed motion of stars. Simulations using only stars, gas, and dust lead to galaxies that behave differently from what telescopes reveal. These simulated galaxies lack the stability seen in real ones, and their outer regions begin to drift apart. When dark matter is added to the model, the results align closely with observations. The gravitational field produced by the unseen mass provides the necessary support to maintain the galaxy's shape and regulate its internal dynamics. The stars move as they do because the halo controls the gravitational landscape they travel through. Beyond the scale of a single galaxy, dark matter continues guiding structure in ways ordinary matter cannot. Galaxy clusters, some of the largest gravitationally bound objects in the universe, contain vast amounts of dark matter that exceed the mass of all the visible galaxies inside them. The dark matter forms the underlying gravitational framework of the cluster, determining how galaxies move within it and how the overall structure evolves. Observations of clusters show that their mass distributions rarely match the locations of visible matter alone. Instead, gravitational lensing reveals broad regions of mass that extend far beyond the glowing galaxies. These extended regions highlight how dark matter shapes the cluster's entire environment, pulling galaxies together and influencing their orbits. Clusters often experience mergers where two or more large structures collide. In these events, dark matter plays a crucial role in how the clusters pass through one another. Because dark matter interacts so weakly, it moves almost unaffected through the collision, following the motion of the galaxies. Meanwhile, gas clouds inside the clusters collide, slow down and heat up, becoming visible in X-ray images. The separation between the gas and the gravitational mass provides clear evidence that dark matter shapes cluster behavior independently of visible matter. The gas responds to collisions, but the unseen mass continues forward, carrying galaxies with it. This behavior reinforces the idea that most of the cluster's mass consists of something that rarely interacts with ordinary matter. Dark matter's influence extends even further, playing a central role in forming the cosmic web itself. Although galaxies trace this large network visually, the structure itself derives from the unseen mass. The web formed when slight fluctuations in density from the early universe grew under gravity. Dark matter, unaffected by radiation and capable of interacting only through gravity, began clustering first, creating long filaments and wide nodes. The visible matter followed these structures once it cooled enough. The positions of galaxies across billions of light years reflect the layout of the dark matter network. Even the sizes of cosmic voids, the regions with few galaxies, depend on how dark matter gathered in surrounding regions. If the properties of dark matter were even slightly different, the entire web could have formed another way. If the particles moved faster, small structures wouldn't have formed early enough. If the particles moved too slowly or interacted too strongly with one another, the structures might have clumped too tightly. The balance seen in the universe reflects dark matter's specific behavior, a combination of weak interaction, moderate motion, and gravitational influence. This combination allowed the universe to evolve toward the distribution of galaxies observed today. In addition to shaping where matter accumulates, dark matter influences how galaxies grow. When two galaxies collide or merge, their visible components can pass through one another, interact, or form new stars from disturbed gas. But the underlying halos of dark matter merge in ways that determine the eventual shape of the combined system. The halos draw material inward, reshaping the gravitational field and guiding how the visible galaxies settle over time. Many of the features seen in large galaxies today, such as extended halos of stars or streams of disrupted material, reflect the history of interactions shaped by dark matter halos. These halos preserve the memory of past mergers, influencing how stars and gas distribute themselves long after the visible remnants have dispersed. Even in regions far from galaxies, dark matter continues shaping gravitational environments. For example, the motion of satellite galaxies orbiting large ones depends on the mass of the halo they inhabit. Observations of these satellites reveal gravitational pulls far stronger than visible mass can explain. Dark matter provides the invisible anchor that keeps these smaller systems bound. In some cases, the distribution of dark matter determines whether a satellite galaxy remains intact or becomes stretched into elongated streams. These tidal features help astronomers map the extent of the halo, giving insight into how far it reaches beyond the visible boundaries. Another example of dark matter's influence involves how galaxies cluster together. Gravity pulls galaxies into groups and clusters, but the rate at which they gather and the distances they maintain depend on the total mass in the region. Only by including dark matter can simulations reproduce the observed clustering patterns. The structure of galaxy groups, their shapes, and their motions all align with models that assume large amounts of unseen mass between and around the visible galaxies. Without dark matter, the clusters would be weaker, less organised, and slower to form. Dark matter also affects the expansion of the universe. Although dark energy drives the acceleration of expansion, dark matter contributes significantly to the total gravitational pull within the universe. The balance between dark matter and dark energy shapes the rate at which structures form and grow. If dark matter were absent or had different properties, the universe's expansion history would look entirely different. Galaxies might still form, but their timing and distribution would shift noticeably. The cosmic microwave background also reflects this balance. The temperature fluctuations in the background provide a snapshot of conditions in the early universe, showing how matter clustered at that time. These fluctuations depend heavily on the amount of dark matter present, and measurements align closely with a model that includes far more dark matter than ordinary matter. Despite dark matter's widespread influence, it never meets us in a conventional sense. It doesn't interact with atoms in a way that allows detection through chemical reactions or electromagnetic forces. This lack of interaction means that dark matter passes through Earth continuously without being noticed. Its particles move through the planet as if it were mostly empty space. They continue into the atmosphere, the crust, the oceans, and even through our bodies without leaving tracks. Detectors built to measure their presence rely on rare collisions that might occur only once in months or years, even when using large volumes of sensitive materials. The fact that dark matter shapes the universe without interacting with our surroundings creates a unique situation. It is both intimately connected to everything and completely separate from the daily experiences of life. The stars form because dark matter made their galaxies possible. The motion of the Milky Way through space follows the gravitational pull of unseen mass. Even the long-term future of the universe depends on the balance between dark matter and dark energy. Yet none of these effects appear in ways a person would notice directly. Gravity works over enormous distances and long timescales, making dark matter's effects visible only through careful measurements and observations. This separation between influence and interaction creates challenges in studying dark matter. Because it refuses to engage with visible matter except through gravity, every attempt to understand it requires indirect methods. Astronomers observe motion, lensing, and structure formation to map where it is. Experimentalists build detectors hoping for rare collisions. Theoretical physicists explore models that predict how it might behave if new forms of matter exist. Each approach captures a different aspect of the phenomenon, but none provide a complete view. Dark matter shapes everything while remaining silent about its own identity. Even so, its influence provides the foundation for nearly every structure in the universe. Without dark matter, galaxies wouldn't form in the same numbers or shapes. Stars might still appear, but the universe would lack the rich web of filaments and nodes that define its large-scale structure. Galaxy clusters would be weaker, and many satellite galaxies wouldn't remain bound. The gravitational balance between galaxies would shift, altering the long-term evolution of cosmic environments. Dark matter doesn't need to interact with ordinary matter directly, because its gravitational role alone reshapes the universe across billions of years. The fact that dark matter determines these large patterns without participating in familiar interactions highlights how much of the universe operates beyond everyday experience. The visible world represents only a fraction of what exists. Ordinary matter produces light, forms planets, and builds the structures we see, but it isn't the primary component guiding cosmic evolution. Dark matter fills that role. Its gravitational influence defines the terrain upon which all cosmic events unfold. Everything else, including the matter-forming stars, planets, and life, develops within the framework established by this unseen mass. The long search for the unseen mass shaping the universe has led to a question that circles back again and again, not because the evidence for dark matter is weak, but because the nature of the evidence invites scrutiny. Astronomers and physicists have spent decades tracing the effects of something invisible, something that governs motion so thoroughly that it has become an essential part of every modern cosmological model. Yet the fact remains that even with this overwhelming consistency, the unseen material has never been detected directly. It has not been captured in a detector, identified in a signal, or observed interacting with ordinary matter except through gravity. This creates tension between what the universe demands and what tools have been able to confirm. In that tension rests an important question. Does dark matter actually exist as a physical component of the universe, or is the interpretation of the observations pointing towards something else entirely, something that hasn't yet been recognized because the assumptions guiding the investigation have shaped the direction of the answers? The question is not rooted in doubt for its own sake. It arises because every attempt to reveal the particles thought to make up dark matter has so far come up quiet. Sensitive detectors buried deep beneath mountains have listened for rare collisions and found nothing. Space-based telescopes have watched for unusual emissions and discovered signals that tend to match ordinary astrophysical processes instead. Particle accelerators have attempted to create invisible particles by recreating early universe conditions, only for results to remain within the bounds of the known physics. These quiet outcomes do not contradict the existence of dark matter, but they raise an important point. If dark matter is a new form of matter, it may be so elusive that it lies beyond the reach of current technology, or it may take a form different from those tested so far. At the same time, the universe behaves in ways that cannot be explained by visible matter alone. Galaxies rotate too quickly at their edges. Clusters hold together with far more mass than they show through starlight or gas. Light bends around galaxies and clusters more strongly than the visible material can account for. Large-scale structures form earlier and more efficiently than visible matter alone can produce. The cosmic microwave background reveals patterns requiring additional mass that does not interact with radiation. These elements appear in different contexts, rely on different measurements, and use different kinds of instruments. Yet they all point toward the presence of something with mass that does not reveal itself through light. This consistency has made dark matter a central pillar of modern cosmology. The difficulty lies in understanding how that pillar is built. The evidence for dark matter is indirect, inferred through gravitational effects. This type of evidence has a long history in astronomy. Neptune was discovered because its gravitational influence tugged on Uranus, revealing its presence before it was seen. In that sense, the logic used for dark matter isn't unusual, but Neptune was eventually observed directly, confirming the model. Dark matter has not reached that point. The gravitational effects are unmistakable, yet the source of those effects remains unseen. This creates a scenario where the existence of dark matter is both strongly supported and persistently unconfirmed at the particle level. Some researchers have suggested that perhaps dark matter does exist, but the expectation of detecting it directly might not match the true nature of the material. It may not interact with ordinary matter in ways that produce detectable signals. It may not collide with detectors, decay into measurable particles, or convert into photons under magnetic fields. It could be a form of matter fundamentally different from anything familiar, requiring entirely new detection methods or theories to approach. If this is true, then the absence of direct detection does not reflect its absence. Instead, it reflects limits in the assumptions guiding the search. Another possibility is that dark matter is not a single type of particle, but a combination of multiple components. The visible universe contains a range of matter types with different properties. It would be unsurprising if the unseen universe contained similar variety. If dark matter consisted of several types of particles with different masses, speeds, and interaction strengths, detecting any one type might become significantly more complicated. Experiments built to search for one interaction might miss another entirely. This scenario would allow for the gravitational consistency observed while explaining why direct detection remains elusive, but it also expands the complexity of the problem, requiring theories capable of describing a hidden sector that might include multiple unknown particle families. In contrast to these ideas, some approaches question whether the unseen mass must be interpreted as actual substance. If gravity changes its behavior under certain conditions, perhaps the observations reflect adjustments in gravitational law rather than the influence of a new type of matter. Modified gravity theories contend that the gravitational pull in low acceleration environments, such as the outer regions of galaxies, does not follow the traditional expectations. If this were true, stars would move more quickly without requiring additional mass. While some modified gravity frameworks reproduce specific observations, they struggle with others. Galaxy clusters in particular remain difficult to explain without additional mass. The cosmic microwave background also provides strong constraints that modified gravity alone cannot fully satisfy, without adding more assumptions. These limitations do not eliminate the idea, but suggest that if gravity is being misinterpreted, the adjustment must be far more complex than initially proposed. There is also the possibility that both dark matter and modified gravity contribute to the universe's behavior. In this view, dark matter exists, but gravity also includes components not accounted for in the simplest models. These hybrid theories attempt to combine the strengths of each approach, explaining why galaxies behave as they do, while preserving the need for additional mass in clusters and large-scale structures. This approach is attractive because it allows flexibility, but it also risks becoming too adaptable, making it difficult to test specific predictions. Still, the idea reflects the broader uncertainty surrounding the true origin of the gravitational effects being measured. The question of whether dark matter exists in the literal sense becomes intertwined with how evidence is interpreted. Astronomers measure gravitational fields, map motion, and observe cosmic structures. These measurements are objective. What changes is the framework used to explain them. The assumption that unseen mass must be matter has guided research for decades, and the results strongly support that interpretation. But the assumption itself remains open to examination, especially if the expected particles continue to remain undetected. If the evidence continues expanding while direct detection remains absent, it may become necessary to reassess what the gravitational effects signify. Another factor shaping the discussion involves the early universe. The cosmic microwave background offers a snapshot of conditions shortly after the beginning, showing how matter was distributed. The patterns in the background depend heavily on the amount and type of mass present at that time. Dark matter models reproduce these patterns accurately. Modified gravity models can do so only by adding additional assumptions or components, often resembling dark matter in behavior. This creates a situation where removing dark matter requires replacing it with something functionally similar. Even if the unseen mass is not matter, any alternative explanation must behave much like it to match the observations. That requirement narrows the range of possible alternatives. One of the more philosophical elements of this question is the recognition that human understanding of the universe has repeatedly expanded when new types of matter or forces have been discovered. At one time, the idea of an electromagnetic field was unfamiliar. Later, quantum fields reshaped the understanding of particles. The discovery of neutrinos revealed a type of matter that rarely interacts, yet exists in enormous quantities. Dark matter, if real, would be another extension of this pattern, revealing that the universe contains forms of matter that play major roles despite being invisible to light. This perspective suggests that dark matter may simply be the next step in the continuing refinement of physical theory. Alternatively, the question could indicate a deeper misunderstanding about how gravity operates, or how mass distributes itself under cosmic conditions. The complexity of cosmic structures might include elements that current theories haven't captured. If dark matter is not a substance, then what the universe reveals through gravity might point toward a more fundamental layer of physics not yet understood. This approach requires exploring models that extend beyond general relativity or beyond the standard model of particle physics. Such models remain speculative, but they highlight that the question isn't resolved purely by accumulating more data. It also depends on developing new ideas that can explain the same observations in different ways. Even the possibility that dark matter is not a single concept, but a placeholder for multiple unknown phenomena remains open. The gravitational effects attributed to dark matter might involve contributions from distinct sources. Some might arise from new particles, others might stem from underlying gravitational principles. Some might reflect early universe physics not yet incorporated into models. If multiple factors contribute to the unseen mass, then searching for one specific type of particle would be insufficient. The quiet results from detectors might reflect this mismatch between expectation and reality. Despite these considerations, the continued success of dark matter models in explaining observations across many scales keeps them central to modern cosmology. From galaxies to clusters to the cosmic web and the early universe, the unseen mass provides a consistent explanation that matches data with few contradictions. If dark matter does not exist, then whatever replaces it must replicate these successes while offering new insights. That bar remains high, and so far alternative models have not consistently reached it. This doesn't close the question, but it indicates that dark matter, whether a particle or something else, remains the simplest solution that fits the widest range of evidence. The question of whether we might be missing the point becomes less about doubt and more about recognizing the limits of current knowledge. Dark matter might be exactly what it appears to be, a form of matter that interacts only through gravity and perhaps the weak force existing in quantities far exceeding ordinary matter, or it might represent a convergence of assumptions guiding research down a particular path, missing other possibilities. The search continues because the universe continues offering clues, each one pointing toward the same gravitational influence while withholding the identity of the object behind it. This ongoing uncertainty doesn't diminish the value of the observations, it reflects the natural process of scientific progress. Large questions often persist for long periods, shaped by cycles of evidence, theory, and re-evaluation. The absence of direct detection encourages refinement of experimental methods. The success of dark matter in cosmological models strengthens the framework guiding new observations. The tension between the two keeps the field dynamic, open to adjustments even as it remains anchored to the gravitational evidence that started the inquiry. All of this leads toward the realization that understanding dark matter might require perspectives not yet available. The solution may come from a new particle, a revised model of gravity, a deeper understanding of early universe physics, or a combination of these ideas. Whatever the answer, the influence of the unseen mass on the universe will continue guiding research, shaping the development of theories, and offering opportunities to explore the hidden structure of the cosmos without ever revealing itself, directly through the familiar signals of ordinary matter. The search continues not because dark matter is uncertain, but because the universe still holds room for deeper explanations waiting to be uncovered.